Assalamualaikum warahmatullahi wabarakatuh and very good morning. First of all, I would like to welcome all of you to the online workshop on the surface ocean lower atmosphere study in the Southeast Asia. My name is Muhammad Khalid Latif, Chairman for this workshop. This workshop is jointly organized by Surface Ocean Lower Atmosphere Study, or SOLAS, together with Idea Center UKM, Marine Ecosystem Research Center, ICOMA UKM, Institute of Earth Science, Ocean and Earth Sciences, University of Malaya, and Sun Yat-sen University, China. A little bit introduction on SOLAS. The global and multidisciplinary research project, Surface Ocean Lower Atmosphere Study, or SOLAS, with its theme linking ocean-atmosphere interactions with climate and people, was established to provide international science coordination and capacity building. Initiated with a first open science conference in 2000 and formally launched in 2004, SOLAS research aimed to understand the key biogeochemical physical interaction and feedback between the ocean and the atmosphere. This workshop aimed to discuss SOLAS-related research and activities in Southeast Asia. We will hear presentation from one keynote speaker, 5 invited speakers, and 7 oral presenters. Without further ado, I would like to invite Professor Fredolin Tangang, Head of Department of Earth Sciences and Environment, Faculty of Science and Technology, Universiti Kebangsaan, Malaysia, and a prominent professor of ocean and climate change to deliver his welcoming speech for this workshop.
Thank you. Thank you, Professor Muhammad Talib. Greeting and good morning, everyone from Kota Kinabalu, Sabah. I'm actually traveling. Fortunately, the internet line at the hotel here seems to be very good. So, welcome everyone, the speakers, the participant to this online one-day workshop on surface ocean lower boundary atmosphere study, SOLAS, Southeast Asia. Professor Dr. Muhammad Talib, Chairman, Sustainable Resources, Environment and Smart Living Research Cluster, Idea Center, and also SOLAS, Scientific Steering Committee member. Professor Zhiyu Liu, one of the keynote speaker and representative for Professor Minhan Dai, SOLAS co-chair, which I was told that are not able to join us today. Professor Dr. Zaidi Cekub, Head of Marine Ecosystem Research Center, or ICOMAR of UKM, representative from International Project Office, sponsors, invited speakers, professor, participant of this one-day SOLAS workshop. Welcome everyone. On behalf of the Department of Earth Sciences and Environment, I would like to welcome everyone to this workshop, online workshop. Unfortunately, we are still grappling with the pandemic, although in some places, face-to-face workshop or face-to-face conferences are already beginning to happen. 2 weeks ago, I was in Vietnam. Seems to be people not really, care so much about COVID anymore. But in some other places, of course, this is still a real concern, a real threat. And with technology these days, we can, have as good as online workshop as good as a face-to-face workshop. So many thanks to Professor Zhiyu from Xiamen University that I'm willing to accept, who has accepted the invitation as a keynote speaker, invited speaker, and all oral presenters to this workshop. I was informed that the aim of this workshop basically to highlight the main finding on the surface ocean and lower atmosphere study and initiate research collaboration among scientists in Southeast Asia to work together on research related to the surface ocean and atmosphere study in Southeast Asia. So this is a very important research, and you're talking about oceans, you're talking about atmosphere, huge area, and collaboration among countries, collaboration among scientists in this region is very important. As a scientist that focuses on research on climate change, particularly in Southeast Asia, I encourage this kind of effort by SOLAS project and co-sponsors of this workshop, including the Center of IDEA UKM, Marine Science Research Center ECOMAR, Universiti Kebangsaan Malaysia, Institute of Ocean and Earth Sciences IOES, University of Malaya, and Sun Yat-sen University in China. Southeast Asia is a region that is important for the surface ocean and lower atmosphere study. Its tropical condition with high temperature and humidity influence the interaction between the surface ocean and atmosphere. With the unique climate condition, there are many research questions related to the influence of land, natural and anthropogenic on ocean and its influence on the atmosphere in this region. With this opportunity, I would like to thank all participants that have registered for this workshop. Last but not least, I would like to say thank you to all and congratulations to all the local and international committee members that contribute to the organizing of this one-day workshop. I hope all of you would have a fruitful discussion, fruitful deliberation for this workshop, and I hope this won't be the last. There will be hopefully many workshops in the future. So thank you, Professor Talib, for inviting me, and thank you all.
Thank you very much, Prof. Fredolin, our head of department at Universiti Kebangsaan Malaysia. Now, I will invite our first keynote speaker. The topic of presentation of our keynote speaker is SOLAS Science, a Regional Perspective and Opportunity. This presentation is combination of talk by Professor Minhan and Professor Zhiyu from Xiamen University, China. Due to the Professor Minhan has another important commitment, this talk will be presented by Professor Zhiyu from Xiamen University. I think before that, I will introduce both presenter, Professor Minhan and also Professor Zhiyu. Professor Minhan is a chair professor of marine biogeochemistry at Xiamen University and an academician of the Chinese Academy of Sciences. His primary research interests are ocean biogeochemistry and sustainability, and he led 2 China Coastal Carbon Program since 2009 in the framework of 973 programs. and is leading NSF major project entitled Carbon Fixation and Export in the Oligotrophic Ocean, or Carbon FE. He has published over 200 papers in leading international journals. Professor Minhan has served on many national and international committees. He was a member of the advisory board of the Ocean Acidification International Coordination Center, or OAICC, and he is a member of the expert group of the high-level panel for sustainable ocean economy and a member of the China Council for International Cooperation on Environment and Development, CCI-CED. He was co-chair of the program committee of the Oceans 19 conference, and he is currently co-chairing the international program Surface Ocean and Lower Atmosphere Study of SOLAS. He was awarded a OGS Export Medal in 2022. Professor Zhiyu Liu is a professor of oceanography at Xiamen University. He is currently served as an associate dean of Xiamen University College of Ocean and Earth Sciences, or COE, and associate director of the State Key Laboratory of Marine Environmental Science, of MEL, and the associate dean of the China ASEAN College of Marine Science of Xiamen University, Malaysia. He specialized in fluid turbulence and ocean dynamics. His research focused on turbulence and mixing in the ocean, including the characteristic, mechanism, impact, and representation in numerous ocean and climate models. This naturally comprises studies on dynamical instability of ocean flows, identification and characterization of key mixing processes in different regimes of the ocean, and development of mixing parameterization for numerical model of various degree of complexity. He is currently an editor of Geoscience Letters, Journal of Oceanography and Ocean Dynamics, and associate editor of Frontiers in Marine Science, and an assistant editor-in-chief of Acta Oceanologica Sinica. He was awarded the NSFC Excellent Young Scientist Fund in 2016 and received the Outstanding Young Talent Award via the National High-Level Talent Special Support Plan in 2020. He created and led Xiamen University Dynamical Oceanography Group towards advancing dynamical interpretation and prediction of multi-scale oceanic process and phenomena. Without further ado, I would like to invite Professor Zhiyu Liu to present his presentation.
Okay, thank you very much, Professor Luti, for the kind introduction. Can you hear me? Can you hear me?
Yes.
Okay, good. First of all, I would like to apologize on behalf of Minhan for his absence today, because he has really urgent, very high level administrative meeting to attend today. So I would like he asked me to give this talk on behalf of him. But I need to point out that because Minhan, as Professor Latif introduced, he's a biogeochemical oceanographer, but I'm a physical oceanographer. So, and also obviously Minhan has a more broad view on solar science, as well on marine science in general. But my research mainly focuses on ocean dynamics. It's fine. So today, the title of my talk is Solar Sciences, a regional perspective and opportunity. So with this, I would like first to have a brief introduction to SOLAS, the organization and science we pursue within this project. And after that, I would give you my very personal perspective and in terms of solar science in our region, the Southeast Asian region, and for some opportunities, and particularly for international collaborations between within the SOLAS community. As Professor Latif introduced, I currently work in the State Key Laboratory of Marine Science in Xiamen University. And I also work in Xiamen University in Malaysia, and we have a college of called Chinese Ocean College of Marine Science, which is a teaching and research platform for international collaborations, particularly within Southeast Asia. So I would like to see, in future we can have a different kind of collaboration, either in education or research. Okay. So the mission of SOLAS is well defined. Is we try to quantify and understand the physical biochemical interactions and also the feedbacks between the ocean and atmosphere, and also how this coupled ocean atmosphere system affects and is affected by climate and global change. So now is the second phase of SOLAS. We are starting from 2004, I think. SOLAS have been running now nearly 2 decades. And for now, we have a scientific steering committee consists of 17 members from 14 countries. As you can see here, we have quite a broad coverage here, and we have scientists from different countries, different part of the world, basic, and with different expertise. And as you can see here, Professor Latif is also a member of the scientific steering committee. So, so basically, the projects are led by this committee, and particularly design the scientific strategy plan, as I will introduce later on. So for the operation of SOLAS, we at present we have 2 IPO, International Project Office, one in the National University of Ireland at Galway, and one in Xiamen University here. At Galway, we have 2 we have 2 staff and led by Jessica, and here also in Xiamen led by Li. And starting from this year, I think we also have a SOLAS Structural Research Master Program. It's hosted by National University of Ireland at Galway, and have a lot of interactions with SOLAS scientists. The SOLAS is represented by 31 scientific networks with 33 representatives from different parts of the world, either as a steering committee member or as national and regional representatives. So as you can see again here, we have a network, a really global network. So it's well connected with different parts of the world. And also SOLAS is well connected with other other international projects like what you can see here, AMBER, and also CLIVER, all this kind of PICES. So it's well connected with different international projects within the earth sciences and atmosphere and ocean sciences. So from here, you have we can have different topics, and we have running different collaborations with different organizations, and so which we can cover. We can interact with more scientists from the globe, and also SOLAS sponsor and endorse many projects. For example, currently here in East Asia, we have the Carbonate, which led by Minhan, and we're basically working in the North Pacific subtropical gyre physical biochemical interactions, and it's ongoing projects. And there's many others in the different parts of the world. And also for the oceanography, now we have a UN decade, so United Nations Decade of Ocean Science for Sustainable Development from last year to the end of this decade. So SOLAS also commit to this action. So we have different activities along with this UN decade program. And one of the key events of SOLAS is the SOLAS Open Conference. And we already had 7 over the last nearly 20 years. And the 8th will be in Cape Town in South Africa later this year. Later this year, yes. So another key event of SOLAS is the SOLAS Summer School, which is very good actually. I participated one of them in 2013 in Xiamen. So this is a very good platform, very good program to bring all the students from different parts of the world to have intensive training for this summer school. Again, we already had 7, and the next one will be online, unfortunately, in Cape Verde. Very recently, we also launched the SOLAS seminar series, and as you can see here, we already had 2, and with different topics. So the idea of these seminars would be to foster discussions on cutting-edge scientific questions, providing researchers at all career stage with the opportunity to interact and build SOLAS community across the globe. And currently, we call for the host for these seminars. If you like to host a seminar, please contact with Lily to initialize this seminar. I think that's a very good way to, particularly during this pandemic. We're still in the pandemic situation. So in many parts of the world, so it's very nice way to gather to exchange ideas between scientists. And we are, if you want to know more about SOLAS, if you want to attend different conference events, and please try to commit with us. So this is just a brief introduction to SOLAS, and later on. So for the science, it's for the just not for the general introduction to SOLAS. So in terms of science, SOLAS has 5 core themes for the second phase. As you can see here, is summarized in this it's a figure. So the first one is greenhouse gases and the oceans, and the second is energy interface and fluxes of mass and energy, and we also have atmosphere deposition and ocean biology chemistry, interconnections between aerosols, clouds, and the marine ecosystems, and also ocean biological controls on atmospheric chemistry. So these 5 things are interconnected, and as you can see here, particularly for the second phase, I think is focused more on biological chemical parts. And as I will explain later, I think probably during the next stage, we should re-emphasize again the dynamics, which I will explain later why we need to. I think for at least from my point of view, I think the SOLAS now is more focused on biogeochemical and atmospheric and ocean, of course, interactions. However, these interactions are also strongly influenced by the physical processes.
Okay, the first one is on the greenhouse gases and oceans. In the atmosphere, we look at the transport of these gases and also their chemistry. And in the upper ocean, we look at processes like ocean acidification and deoxygenation and evaporation, and also in detrification of this kind of processes affecting the greenhouse gases. And the second part is look at physics as interface of the atmosphere and upper ocean. So with the goal of quantifying the fluxes of mass and energy and material through the LC interface. And here you can see here is focused on upper ocean dynamics. Look at the turbulence generation in particular due to the atmospheric forcing like the wind and the buoyancy and also the surface waves. The third theme is atmospheric deposition, ocean biology chemistry. So particularly look at how this atmospheric deposition affects the upper ocean biochemical processes. And the first is interconnection between the aerosols, the clouds and the marine ecosystem. Particularly, we look at the material transfer from the ocean to the atmosphere, which affects the aerosols, and also how these aerosols affect the formation, for example, of a cloud, and then they fed back to the marine ecosystem. And also we look at the ocean biochemical controls on atmospheric chemistry. This particularly look at how material from the ocean affect the aerosols and affect the chemistry of the atmosphere. On top of that, we also have several cross-cutting themes. For example, we have the integrated topics which look at the upwelling zones, polar oceans, and Indian Ocean, and we also have other topics. And this is a general introduction to the solar science, but how what does it mean to the Southeast Asia region? So as a physical oceanographer, I will further to emphasize a few key points that in our region, what kind of science we can possibly pursue, and particularly from the physical part, and also I will lay some background for the physical biological interaction studies that we may have international collaborations on these topics. The first thing I would emphasize is ITF, is Indonesia through flow. This is basically the up ocean branch of the so-called ocean conveyor belt. Of course, the real ocean dynamic, ocean circulation is much more complicated. Particularly, we have a lot of eddies in the ocean, so we really have a eddying or even turbulent ocean instead of the simple conceptual model by famous biologist Wally Burke several decades ago, like I'm showing here, is so-called ocean conveyor belt. But after the ocean, this part of the ocean, particularly Indonesia seas, is important pathway for the water from the Pacific to the Indian Ocean. As you can see here, the water change. This is, by the way, showing the temperature and the salinity on the ice signal. So they have the same density, and basically this is how the water flows in the ocean. So you can see the water flowing from the Pacific to the Indian Ocean, and it's gradually changing the salinity, basically increasing the salinity because of the mixing with ambient water. So this channel is very important globally, and so this is a basic connection between the Pacific and Indian Ocean. This has a great global significance in terms of ocean circulations. So this is and in particular, as you probably noticed here, in the Indian seas we call a mixed master, as I'm showing here. Actually, this place is Indonesia is the hotspot of tidal mixing. That's why how the water mass from the Pacific to the Indian Ocean, not simply by transport, but water is also transformed from, meaning they are changing their properties of like temperature, salinity, and the nutrient content. That's how this water transformed from the Pacific to the Indian Ocean due to the storm making in this Indonesia seas. That's why it's called Indonesia mixed master. So the idea here is we have a very, like you're showing here, and this is very interesting plot by Jan Sprinter. You see here from the Pacific part to the Indian part of the water. You see, if you look at the TS diagram, you see the water mass gradually changing the properties. It's the clear signature of the water is gradually mixing, and actually the subsurface of some kind of water can upward to the surface, and that's why they see they can participate in LC interactions. And the driver here is the tides, because we have strong tides in this region, and because we also have a complicated topography, they generate so-called internal tide or barrier tides. And these tides then cast energy to small-scale turbulence, which eventually induce strong mixing. Showing here is the numeric simulations, and you see very strong mixing in this region. Now, although we have this kind of conceptual understanding of this process, but a lot of unknowns, for example, the regional distributions of mixing, and also even the process of mixing, and their permutation, the climate and ocean models remains a big issue. I think in the future we could possibly have collaborations in this on this problem. And in fact, not only this, including the Tachanat Sea showing here, you see there's a lot of process going on here, eddies, internal waves, and like I summarized in here. So we here you can look at different process. We call that a multiple scale dynamic process. We have the forcing from the typhoon, for example, from a monsoon. We have the atmosphere driver driving the circulations, and they have different scales of process like eddies, internal waves, and internal tides, and small scale turbulence. So this part of the ocean is really a natural laboratory for studying multiple scale ocean dynamics and the cascade mixing, and also physical biogeochemical interactions, even they affect the climate, global climate, and also ecology. And as another interesting feature, or most important feature of our part of the ocean, we have the Indo-Pacific warm pool. This actually is the heat engine of the globe. So for the global climate, the highlight, particularly for the Atlantic, for example, is a switch of the climate. But in the low latitude of the ocean, in our part of the ocean, because we have a big body of warm water, so they have a lot of evaporations. They have a lot of heat or energy released from the part of the ocean. The driver basically the global climate system, and so this is why it's called a heat engine of the globe. So air-sea interactions, air-sea heat flux, and also freshwater flux is very important for the global climate. And also here we have famous interannual variabilities like El Nino and LD. Showing here, you can see we have, due to the evaporation of this hot water, it drives the deep atmospheric convection, which further drive the Pacific work circulation, which basically set up the large scope wind pattern in this field. And also you can see here, for example, the INSO influence. Basically, when INSO occurs, basically you shift the warm water mostly zonally. So you can change the location of the warm water. That's why you change the location of deep convection. And then it affects the rainfall, of course, and other aspects. And you can see this signal, this impact can cascade to the deep part of the global ocean and the land. So this have a dramatic impacts on the global climate. And also the system here is a Sunda monsoon system in terms of the ocean processes and climate and ecology. Showing here, you see due to the change of from the summer monsoon to the winter monsoon, you change the upwelling to the downwelling. When the upwelling occurs, you see more nutrients at up oceans. That's why you have a higher chlorophyll here. It means the higher biological productivity. And of course, the entire system, including the ITC, the inter-hemisphere convergence zone, also change seasonally. So the entire system here has a dramatic seasonal changes. And interestingly, we also have the coral triangles. This is the basic water epicenter of marine biodiversity. So if you look at the fish, corals, snails, and lubbers, you can see there's really a center of the different biologies. So you see, this is a really species different. This triangle obviously is very important to the global ecology, and also they are very sensitive to climate change. So there's a lot of ongoing efforts to look at this region, how, for example, the corals adapt to the climate change, global warming, ocean acidification, or process like this. I think this also a good topic for further collaborations. And even the fish catch, showing here is the skipjack tuna catch. And you can see here that the tuna catch has a close correlation with the change of SOT. Shown here is basically the ST, because as I mentioned, is interannually is modulated by INSO. And also you can see here the tuna catch also has a interannual variability, and basically the center of the catch follows the 28 ice lines. So basically isothermal. So it means that as you change the location of the salinity front and temperature front, you change the fish catch. Interesting here, because in this region the primary productivity is low because there's not much nutrient, but the tunas can have a large catch. It means that there must be maximum transport is tuna from for example, from the eastern and equatorial Pacific to the western equatorial Pacific. And so if we look at the CO2 studies, and this is a very famous Takahashi plots, you can show in here the global PCO2, and you will notice that in our part of the region we have very less data, and even including this anthropogenic CO2 also we have much where the observation is very sparse. And so this, but luckily, recent years we see collaborative studies between, for example, China and Indonesia. We have some cruises start to look at the air-sea fluxes and this kind of biochemical processes in this region, and they are already suggesting regional features. And this showing here is the recent folks we have been pursuing. This is a big project, ongoing project called Carbon-free led Minhan Dai. The idea is inspired by our previous studies in Tachanat Sea. Basically, we are using this turbulence observation and high resolution nutrients observation. So for the first time, we can quantify actually the nutrient fluxes in the upper ocean. And from that, we propose that there are two layers. It's called NDL and a nutrient depleted layer and a nutrient rich layer. So repleted layer. So basically, we try to disentangle the coupled physical biological systems, geochemical system in the upper ocean. So currently, the project's basically we from the idea from the Tachanat Sea, we propose this concept model, including different parts of the different elements and different part of the ocean, and we intend the idea, we test the idea to in the not specific subtropical dry to see whether it works, and we also look forward to test it in other part of the ocean. The last part of my talk would focus on the upper ocean dynamics, and as I mentioned, for the second phase of SOLAS, we have the we have the same on air-sea interface and flux of mass energy. But because over the last 10 years, actually, the upper ocean study has a big, I think the most important progress is on study on some mesoscale processes. Because previously, as we was showing here, when we think about the upper ocean dynamics, particularly affecting the air-sea interfaces, we basically assume the process 1D is vertical processes. But actually, over the last 10 years, we have increasingly realized that in the upper ocean we have a lot of fronts. Basically, you cannot take the upper ocean as a 1D column. Instead, you need to look at interactions or impact of the lateral gradients of, for example, density, temperature, salinity. And so this is called some mesodynamics. They are mostly occur in the surface mixed layer, as I said. So this is exactly the focus of SOLAS, the contact part between the ocean and atmosphere. So they have a relatively small scale. And if you look at the observations or nowadays very high resolution simulations, to see our ocean is filled with this kind of eddies, fronts, filaments, not like what one would assume the upper ocean is basically very calm with very large scale patterns. So if you start to quantify the impact of this mesoscale, you see, for example, showing here is some mass contribution to vertical heat flux in the upper ocean. You see, for example, you see if you look at the plot here, particularly in the west boundary currents regions, you'll see their contribution to the heat flux is huge, and compared with the surface air-sea fluxes. For example, the value can reach up to 200 watts per meter square. So this is huge contributions, not only to the heat budget, but also to the upper ocean biology. And obviously, you can imagine that this process would affect all the theme, all the questions we care about upper ocean, because it seems that some mesoscale process affects the upper ocean and biological and geochemical, biological and chemical processes dramatically. And this shape, in particular, I think over the last probably 5 or 3 years, there's a lot of argument still some debate on this topic, but it seems now it's consensus that this semester particularly affects the biodiversity in the upper ocean. And I just because with considering this audience, probably many scientists are working on the biochemistry, not the physics. So I just give you some ideas in how this some mesoscale eddies or features are generated in the upper ocean, why they are so important. So one of the things is we have the wind forcing and we have upper ocean front, the wind and the front interactions, they generate these features. Basically, the operation stratification is set by a competition between the vertical mixing, which induced by atmospheric winds and buoyancy flux. This is a look at more traditional by ocean dynamics and also within our SOLAS research field. However, we also have the restratification effect from the submeso scale ocean turbulence. They are not small scale turbulence. They are submeso turbulence. They are basically induced the adiabatic process, not diabatic processes. So they change the location of the front, and they induces a lot of some features, and particularly induce very strong upward or downwelling or vertical motions, which bring nutrients up and down. That's why they affect the up ocean productivity substantially. One of the process is called mixed layer volcanic instability. Okay, so because the front we have a generation of eddies, and these eddies and like here along the front you have the front dynamic and stable. They have eddies. That's why, and by generating that they induce vertical and horizontal motion, which bring nutrients, for example, and also planktons and in this water column. That's why they affect the entire food chain in the upper ocean and change the community structure. And also another important process is called symmetric instability. And basically they induce like a lot concepts here showing the ice signal you're showing along the ice signal motions. And also this also important process to induce this material, including the planktons, are transported along the ice signal. That's why they can change the vertical location. That's why they change the for example, the light conditions, and that's why they affect the structure, and also they change the community structure in particular. This is my last slide. So this the existence of this mesoscale processes, and particularly increasingly realized in the last 13 years, pose important challenges for our numerical modeling. And of course, also for our process studies, because these processes are very short time scale, and they also have very small length scale. And in terms of their dynamics, they are both balanced and mixed with balanced and balanced dynamics. That's why it's difficult to predict and to study and quantify theoretically. And they have because they are basic occur in the mixed layer. That's why they can directly feel that fear. That's why they can participate in the direct as interactions, and in order to quantify more actually the LC fluxes and even how the lower atmosphere transport. So we need to study some mesoscales. And also, if you look at the global simulations of climate models, our mixed layer depth is still have a shallow bias, and also obviously as the sea surface temperature also has temporal bias. So just to conclude, so to move the solar science, I mean the dynamic part forward, we need to in the future include some mesoscales. And also I hope that the scientists in other fields, for example, about looking at other parts of solar science, biochemistry, and even biology, they need to realize that in the upper ocean we have these very important processes which need to be integrated to our understanding to better understand and to project the change of upper ocean and lower atmosphere. So I can stop here. Thank you much. I'd like to take questions if time allows.
Thank you very much, Professor Liu. Due to the limited time, whoever has question to Prof. Liu, maybe you can put into our chat and we will forward to Professor Liu.
Yes,
so
please.
Thank you very much for the introduction on SOLAS activities, and also specific work has been done in Southeast Asia and potential work can be done in Southeast Asia. So thank you very much once again. If you have any questions, we can put into our chat and we proceed to Prof. Liu. Thank you very much, Prof. Liu.
Thank you. Bye.
So I pass this presentation to Dr. Tachanat Bhatrasataponkul from Burapha University to chair the talk by Prof. Bala.
Hello, everyone. So Let me briefly introduce myself. Once again, I'm Tachanat. I will be a moderator for this morning session. And we have 6 talks today in the morning. We will starting with Dr. Bala, and while we are waiting for sharing screen, let me briefly introduce Dr. Bala. Dr. Bala is professor and deputy head at the Department of Civil and Environmental Engineering at the National University of Singapore. He received his PhD in atmospheric chemistry from the University of Miami, United States. His expertise include urban air quality, climate change, aerosol science, and environmental sustainability. He has authored more than 250 referee journal publications with more than 18,000 citations. In recognition of his outstanding research contribution, Dr. Bala has honored with numerous awards, including Alan Berman Research Publication Award from the U.S. Department of Navy, highly cited research article award in atmospheric chemistry and professional and scholarly excellence award. He is an elected fellow of the Royal Society of Chemistry, and today he's gonna talk about ocean acidification, known and unknown. Please, Dr. Bala, the floor is yours.
Yeah, do you see my slide?
Yes, please.
Great. Yeah, thank you for the kind introduction. Good morning, good afternoon, and good evening, wherever you are. To start with, I want to thank Talib and Lily for inviting me to give this talk. Well, as you know, the ocean and the atmosphere are strongly coupled with each other with a constant flux of gases, particles, and heat being exchanged between these 2 reservoirs, triggering complex biogeochemical cycles, which are very hard to understand. And hence, the SOLAS program puts a large emphasis on this kind of interaction taking place between the ocean and the atmosphere. So this interaction is particularly important in the context of understanding ocean acidification. So what I intend to do in my talk is to provide give a broad background introduction to ocean acidification, and then talk about the implications of ocean acidification on various scales, and then point out some of the knowns and unknowns. So based on which I would raise certain research questions that need to be addressed by the research community through collaboration. And then I will provide a framework as to what kind of research projects that we could consider pursuing through collaboration. And finally, I'll make a summary of the key points. So this is going to be the outline of my talk. Now, one of the well-known examples of air-sea interactions is the so-called water cycle. While especially during the day, with the absorption of heat, we have the evaporation of water in the form of water vapor going into the atmosphere, forming a thick blanket of clouds, which would eventually lead to rainfall. So basically what goes up eventually comes down, completing the cycle, so-called water cycle. At the same time, we also have such a phenomenon happening with respect to gases and particles. There's a strong linkage between the atmosphere and the ocean. But the difference over here is that it's important for us to consider the chemistry of the atmosphere and the prevailing dynamics we have in the atmosphere, and couple it with the chemistry of the ocean, as well as the dynamics taking place in the ocean. But the dynamics involved in terms of mixing patterns, especially in the ocean, it's very, very complex. For example, we may have constant upwelling and then downwelling of water across the vertical column. And we may also have stratification, which could inhibit the mixing of water in the vertical direction. As a result, dissolved oxygen concentration might even decline, leading to a variety of biogeochemical impacts. So we have started working on this problem in terms of understanding and providing insights into air-sea interactions more than 10 years ago in Singapore. And one of the problems that we tried to address in our research was the coastal eutrophication. And of course, the runoff that we have from terrestrial surface will contribute to coastal eutrophication. But what remained unknown at that point in time, more than 10 years ago, is the importance of atmospheric inputs in terms of nitrogen and phosphorus, the major nutrients, as well as micronutrients like potassium, which could trigger a coastal algal bloom. And in this part of the world where we are, from time to time, we have uncontrolled forest and peat fires, which will lead to emission of nutrients apart from carbon. And those nutrients are likely to be deposited onto the ocean in the form of dry deposition and wet deposition as well. So what we tried to do was to provide, to get a kind of qualitative understanding of this phenomenon in terms of the importance of atmospheric deposition of nutrients onto the open ocean in the context of coastal eutrophication, and then also quantify the inputs in terms of the contribution, the relative contribution of atmospheric deposition to coastal eutrophication. And so we did this study during haze episodes, smoke haze episodes, as well as in the absence of smoke haze episodes. So based on which we were able to differentiate and quantify as to how much of increase in atmospheric inputs we would have during the occurrence of smoke haze episodes. So we published a series of papers on this topic, and two of these papers are highlighted over here, which appeared in well-known journal ACP, Atmospheric Chemistry and Physics, more than 10 years ago. So now we are interested in understanding the importance of ocean acidification. Now, in this context, basically carbon dioxide would come from various sources, of course, from the burning of fossil fuels that we know. And apart from that, CO2 can also be derived from deforestation, which is happening as a result of urbanization, mainly due to population growth. In addition, because of changes we have in agricultural and land use patterns, we have further emission of carbon dioxide. So when the carbon dioxide is emitted into the air, it tends to accumulate, and part of the CO2 is taken up by the ocean, which would lead to the dissolution of carbon dioxide, forming the well-known carbonic acid, which undergoes dissociation, releasing protons, and hence an increase in ocean acidification. At the same time, because of global warming, part of the heat is also absorbed by the ocean, and that warms up the ocean at the same time. So now it becomes rather complex to understand and predict the extent, duration, and the impact of ocean acidification, because the change in temperature of the ocean together with the change in the chemistry of the ocean. But the ultimate goal here is to make a prediction in terms of the potential impacts of ocean acidification on a variety of marine organisms, including coral reefs, which are mainly concerned about. Now, on the left-hand side in figure 1, you could see that the carbon dioxide flux could be bidirectional. So what it means is that although the ocean can act as a massive sink for the uptake of carbon dioxide, it can also act as a source especially when you have strong upwelling and when you have a high temperature of the surface of the ocean. So then some part of the CO2 that was absorbed by the ocean could be released back into the atmosphere. So this bidirectional flow of CO2 complicates this issue in terms of ocean acidification. But in any case, you could see kind of the prediction that has been made in terms of ocean acidification starting from the pre-industrial era. At that point in time, we had only very little amount of CO2, about 280 parts per million. So by now, the CO2 concentration in the atmospheres have increased by more than 50%. And you could see the resulting change in the pH of ocean water. When you look at the scale over here, it tends to be more and more acidic with the time, with the increased concentration of CO2 emanating from a variety of sources. So typically, one could say that about 30% of CO2 in the atmosphere could be absorbed by the ocean, triggering the acidification. But down below here, you could see the chemistry that takes place, which is kind of fascinating. So once the CO2 gets dissolved in water, you get carbonic acid. And then the carbonic acid then dissociates, releasing bicarbonate ion and protons, which contribute to increased acidity. So when you have the free protons being available, you could combine with the carbonate we have in the ocean. We have plenty of carbonate in the ocean. And then when the protons combine with the carbonate, it leads to, again, the bicarbonate anion. So as a result, you would expect to see a decrease in the concentration of carbonate, particularly calcium carbonate, which could exist in two different forms in terms of calcite and aragonate. So these two forms of calcium carbonate tend to decrease with the time, mainly due to ocean acidification. So what? Well, suddenly when the calcification capacity of the ocean decreases, it affects the formation of shells and skeletons of a variety of marine organisms. And suddenly ocean acidification would affect various habitats. Now, in terms of making a prediction as to how the ocean acidification can happen with the time, some work has already been done and published in the literature. So you could see the color change. And right on top, this is the kind of pH of oceans we had back in 1850. But by the end of the century, you could see a dramatic shift in the color over here, indicating that ocean acidification becomes more intense and will become more intense in the future compared to the past. At the same time, on the right-hand side, you can again see the calcification phenomenon. So basically, the saturation of calcium carbonate, and the color change here is becoming more and more brown with the time. So you could see that on top, the color scale indicates that the brown color is reflective of the decrease in the saturation of calcium carbonate. So this is one of the impacts of ocean acidification, and the level of saturation of calcium carbonate is very likely to decrease rather sharply with the time, as projected by this research group, and the paper appeared not too long ago. Now, in terms of understanding and the chemistry of the ocean, especially in the context of ocean acidification, you could see as to how complex it is. Now, to start with, of course, the CO2, like I mentioned before, about 30% of CO2 could be absorbed by the ocean, leading to an increase in the concentration of DIC, which stands for dissolved inorganic carbon. But at the same time, we also have the rivering inputs into the runoff, introducing dissolved organic matter. This organic matter also undergoes dissociation, releasing more DIC, dissolved inorganic carbon, on top of what we are getting from the dissolution of carbon dioxide from the atmosphere. Now, at the same time, the uptake of CO2 induces photosynthesis, leading to primary producers like algae, which would eventually lead to the formation of algal toxins, including some pathogens. So you could see that the ocean gets very stressed on top of the coastal eutrophication that used to happen in the past in the absence of severe ocean acidification. So the problem gets exacerbated because of ocean acidification. Now, on top of it, now you could see here, and when the primary producers undergo a transformation, you produce even more DIC than what we managed to get from the uptake of CO2 by the ocean and from the riverine inputs in the form of DOM leading to DIC. So overall, the concentration of dissolved inorganic carbon in the form of bicarbonate will increase further. At the same time, the absorption of heat, especially the top part of the ocean, we are likely to get stratification. So when you have the stratification, then we don't have much of an exchange of water across the vertical column. So when you have reduced concentration of dissolved oxygen because of the algal bloom being formed over here, we are not able to restore the concentration of dissolved oxygen due to lack of vertical mixing, mainly due to the stratification phenomenon happening. So again, that complicates the issue in terms of understanding and predicting the likely impacts of ocean acidification. So in this picture, you could see the rising concentration of CO2. As I mentioned before, the CO2 concentration, the pre-industrial era used to be 280 parts per million. So now we are crossed 410 parts per million. So the CO2 concentration in the atmosphere has increased by 50% or more by now. But at the same time, you could look at the PCO2 concentration, which is the partial pressure of CO2 in the ocean or in seawater, which is also increasing in tandem with the increased concentration of CO2 in the atmosphere. And the result over here is you could see a decrease in the pH. In other words, ocean acidification increases as a result of the exchange of CO2 between the atmosphere and the ocean, leading to the formation of dissolved inorganic carbon. So in the top 50 meters of the marine ocean, or the ocean itself, and some measurements have been done by a group in 2020. And according to the research findings, you could see that certainly the CO2 concentration increases. Maybe you see the oscillating pattern because of photosynthesis and respiration happening. So it's a kind of oscillation. But overall, there's an increase, exponential increase in the concentration of CO2. At the same time, the CO2 concentration measured in the ocean, the blue color, is also increasing with the same kind of a trend as you see over here. And as I mentioned before, the pH of seawater tends to decrease with the time, reflective of increased ocean acidification. But at the same time, you can also see the decrease in the concentration of carbonate. So which means that the calcification capacity of the ocean is highly compromised because of ocean acidification. And that has a lot of other impacts, which I'll talk about a little later. To sort of put it together in this context, because of ongoing socio-economic activities around the world, we have increased CO2 emissions or increased carbon footprints, which would lead to ocean acidification. And this ocean acidification affects marine ecosystems, including food webs, fish stocks, and coral reefs. More importantly, ocean acidification also disrupts ecosystem services in terms of fish catch, aquaculture, tourism, coastal protection, and loss of biodiversity. And eventually, it affects the economy of countries around the world, welfare, food security, and so on. There's a strong need for us to adapt ourselves to the changing climate. So these are the pathways to consider in the context of ocean acidification. And this picture shows as a conceptual model and that shows basically an overview of the potential upcoming ecological and biogeochemical consequences linking different environmental drivers, processes, as well as cycles. So this conceptual model is important in order for us to be able to make a prediction as to how things might change in the ocean following the uptake of CO2 in the context of biogeochemical cycling that we have been talking about. Now, based on this conceptual model, you could anticipate that ocean acidification would have negative impacts on 4 critical habitats, which would include coral reefs and food webs and carbonate reefs, as well as seagrass meadows. So the arrows here would indicate whether the problem is going to get worse or otherwise, but usually the problem gets worse with the time, as you could see over here. Now, on a shorter time scale, we have also measured the concentration of CO2 up in the air, in water, seawater, and the pH. And you could see as to how the pH of seawater responds to the change in concentration of PCO2, partial pressure of CO2 in air and water. So when the concentration of CO2 increases, you see a sudden pulse, it's a sharp decrease in pH. So there's an instantaneous increase in ocean acidification on a shorter time scale, as you could see. So this kind of diurnal patterns in terms of change in ocean acidification has been well established through in situ monitoring of seawater. To provide further insights, you could see the kind of anti-correlation between the PCO2 concentration and pH. So as the concentration of CO2 taken up by the ocean increases, you see a sharp decrease in pH, and coming from 8 down to even 7.6. So it's a log scale that shows a big change in the concentration of hydrogen ions or protons. At the same time, interestingly, you also see a sharp decline in the concentration of dissolved oxygen as well. So as a result, marine organisms will be starved with no oxygen being supplied for them to absorb. And that could lead to negative impacts on the life of marine organisms. And which is further indicated here as that dissolved inorganic carbon increases, dissolved oxygen concentration decreases. There's a inverse correlation between the two. So certainly the dissolved oxygen is likely to decrease, mainly due to eutrophication related problem triggering by the uptake of CO2. So what are the knowns at this point in time? I just listed all the knowns that, in terms of the understanding we have developed toward ocean acidification. So acidification changes seawater chemical speciation, as I just explained, in terms of the carbonate chemistry, also biogeochemical cycles of many elements and compounds. And we have many trace elements and their compounds which are likely to undergo biogeochemical changes due to ocean acidification or the change in pH. At the same time, and so the effects of this ocean acidification are only being addressed the last 10 years or so. So our understanding is relatively recent. So based on which we could say that ocean acidification is likely to have negative or adverse impacts on a variety of marine species, productive tropical, coastal, and marine ecosystems, and marine organisms as well. So one of the well-known impacts of ocean acidification, as I highlighted a few times, is the lowering of calcium carbonate's saturation states, which would certainly affect the shell forming, skeleton forming of many marine organisms, ranging from plankton all the way to corals, which are particularly important in tropical areas. And which could also, ocean acidification can also lead to the collapse of food webs, and mainly due to the decrease in the concentration of oxygen we have. So, and measurements made at a variety of locations around the world have clearly indicated the kind of relationship between the uptake of CO2 and the resulting chemistry that takes place, followed by the change in the dissolved oxygen concentration, as well as the calcium carbonate concentration or the calcification capacity of the ocean. So what we don't know is what I'm listing over here. So there are many unknowns. So we got several knowns, but we have many unknowns over here. For example, very little is known on the direction and magnitude of CO2 exchange between the atmosphere and the ocean. So you could see over here, the bidirectional flow from based on the amount of heat absorbed by the ocean, we might even release some CO2 back into the atmosphere. So we have to have a better understanding of this potential phenomenon over here. And certainly the impact assessment studies are very important, but they are not very well addressed through research at this point in time. There's a lack of understanding of calcification and capacity of the ocean and the impacts it would have on a variety of marine organisms and their life and so on. So certainly an impact assessment is needed. And so more importantly, we should also be able to project the future trend of ocean carbon sink, especially in the context of net zero that we are talking about, which many countries aspire to achieve by the year 2050. And we don't know, what impact is going to have at that point in time, because the change in the ocean atmospheric coupling with the time. And certainly the decrease in pH or the increase in acidification will in turn increase the bioavailability of certain toxic metals like copper, zinc, and so on, which are harmful to many marine organisms, which would also affect their life and could even shorten their lifespan. So we need to have very high quality data sets on a variety of timescales on many different locations so that we can have a better understanding of the extent of ocean acidification happening and the potential impacts on the marine habitats. So it's important for us to do time series measurements rather than sort of a grab sampling that we tend to do. So if we can do the time series measurements, as I indicated, you could see the instantaneous change in the ocean acidification phenomenon when there's a sudden pulse in terms of CO2 increase in the atmosphere, followed by corresponding increase in the ocean. So based on these unknowns, I have formulated several questions that need to be addressed. For example, what are the CO2 concentrations and the dissolved levels in seawater in many different regions, which are potentially important because of ecological concerns we have, and what are the likely impacts of this change we have in CO2 concentration on coastal and marine ecosystems. And we also need to have medium data sets for us to be able to predict as to how much of a change we would have in ocean acidification, for which we have to also do some modeling in addition to monitoring. So monitoring by itself is not enough. We had to come up with the sophisticated models which can capture the change in chemistry as far as the dynamics of the ocean and couple it with the atmosphere, so we can better understand the potential biogeochemical cycling of trace elements and their compounds and their ultimate impacts on marine organisms. So to fill these knowledge gaps, I'm just making some suggestions for you to consider. And we have to do an innovative research, of course, through collaboration. That's the reason why we have this platform created by SOLAS for us to work together so that we have a better understanding of physical, chemical, ecological, biogeochemical, and societal implications of ocean acidification. You can see here, because of the complexity of the problem, we have to bring in many multidisciplinary perspectives for us to have a better understanding of the impacts of ocean acidification over here. And this knowledge will be very important for policymakers to come up with appropriate policies that will call for proactive actions in order to restore the quality of the ocean we have and hence maintain the life of many many marine organisms. So these are broad research goals, and we should have in mind as we proceed with our research. And basically, the chemistry plays an important role apart from the dynamics. So having said that, this is a kind of research framework that we would like to propose. We have to do an exhaustive literature review depending on where we are to have a better understanding of what work that has been already done and what remains to be done in terms of knowledge gaps. And then we do field sampling and to collect seawater at different locations, at different depths, bring them to the lab and do the measurements, based on which we can also do modeling. Particularly, it's important to do geochemical cycling related modeling by taking into consideration the carbonate chemistry and the dynamics. At the same time, we have to define the boundary conditions under which our modeling predictions will be valid. So these are the key points for us to consider as we move forward in terms of what work that needs to be done in terms of field monitoring, laboratory work, as well as modeling work that will be conducted in tandem with the other aspects of work we do in the lab and in the field. So based on which we can have a better understanding of what needs to be done and so on. So these are the parameters to pay attention to, as I said repeatedly, to solve inorganic carbon that would include alkalinity, pH, CO2 concentration, and the saturation levels of calcium carbonate, including aragonite and calcite, the two forms of calcium carbonate, and temperature, salinity, and suspended particulate matter, organic carbon. All these are related. And we have to also understand the hydrological cycle together. And we have to do in situ measurements of a variety of weather parameters, and then do sampling as well, couple everything together so that we can come up with a large-scale biogeochemical models, which could be applied at variety of regions for us to understand the change in ocean acidification at a global level, as shown in this illustrative diagram. So once you put all the input parameters, output parameters together in this kind of illustrative diagram, becomes an important tool for policymakers to understand as to what needs to be done, which would eventually lead to CO2 mitigation, which is what we are trying to tackle globally, and also protection of many marine organisms, and as well as the adaptive capacity that we need to increase. So having said that, this is for the high uncertainty at the moment in the CO2 flux, because the bidirectional flow, low uncertainty otherwise. So the uncertainty analysis is also important apart from monitoring and modeling work. So we have been also talking about the blue carbon, which is the uptake of the sequestration of CO2 by coastal ecosystems, but it's also important to understand the potential acidification that goes along with it. So this is a summary of my presentation. So future management strategies to mitigate the impacts of ocean acidification should focus on reducing and preventing algal blooms, which would affect the life of many marine organisms due to a sharp decline in the concentration of dissolved oxygen. At the same time, we got to also consider the potential synergistic impacts of nutrient pollution, as I mentioned in my own research done 10 years ago, together with the increased atmospheric deposition of CO2 into the ocean, so that we have a better understanding of potential algal blooms that could occur, which could affect the life of corals and so on and so forth. More importantly, we should also assess, analyze, and predict change in calcification capacity by taking into consideration the change in calcium carbonate concentration and the two forms of calcium carbonate, calcite and aragonite. And so with that, I just end my talk. And finally, it's important to ensure that we provide high quality, reliable inputs to policymakers so that they can take appropriate actions as to what needs to be done to curb the emission of CO2 and restore the quality of marine life. Thank you so much.
Thank you, Professor Bala, for constructive and comprehensive talk. We have room for like one question or two. If anyone want to ask or comments.
Any questions from any of you?
Maybe I
Any
have one.
thoughts, comments to share? If not,
I saw your you show global projection at the end of century, changes in pH highly sensitive at outwelling region. But what happening in Southeast Asia and Bay of Bengal? It seemed to be quite sensitive, like those eastern boundary as well.
yes, exactly. According to the prediction, by the end of the century, in tropical areas, the sea level rise could be as much as 1 meter. Okay, so that's quite increase in sea level rise. That's because of the absorption of heat, and then the melting of ice, and so on and so forth. That in turn would affect the uptake of CO2, and therefore the resultant coastal acidification phenomena. So like I said, everything has to be coupled, right? So we have a framework in mind, and this framework, research framework, has to be expanded in terms of scale of applications, so that we can sort of analyze as to how much of a change in pH of seawater we would have on a much larger scale over a longer time period.
All right, thank you.
Thank you.
We continue some talk under SOLAS core theme 1, 2, and 3. Next speaker is Dr. Faisal Hamzah. He will be talking about the carbonate system in the Indonesian seas. Please.
Thank you, Dr. Tachanat. I will share my screen. Is it clear, my screen? Yes. Okay. Good morning, everyone. My name is Faisal. I am from the National Research in Innovation Agency, Indonesia. Previously, I'm working at the Ministry of Marine Affairs and Fisheries. I'm glad to join this workshop, and today I'm going to talk about the dynamic of the carbonate system in Indonesian seas. This is part of my research study during my PhD at Xiamen University, with collaborate with the Professor Minhan, Professor Dwi Susanto, Professor Sesunwei, Professor Chemian Chow, and etc. The key point of this study, we report the first data set of the carbonate system parameters in Indonesian seas. We divide into 2 regions, Western Indonesia and also along the main route of the ITF. In Western Indonesian seas, homogeneous distribution of the physical and carbonate parameters due to zonal monsoonal winds and shallow water depths, and significant de-ice removal in the upper Sunda Strait. However, along the main route of the ITF, lower values of the carbonate parameters in main inflow than that in the main outflow, and transformation of the ITF materials is in line with the ITF water formation and transport. My talk will include 4 parts. First, I will give you a brief introduction to Indonesian seas and its carbonate system, and I will talk more about result and discussion in part 2 and part 3, and finally give some summary of this study. For the general introduction, why we care about the Indonesian seas. Located in the low latitudes, the Indonesian seas is the only tropical pathway in the global thermohaline circulation, transporting waters from the Pacific to Indian Ocean, known as the Indonesian Truth Flow. During traveling from Pacific, the volume of the heat, fresh water carried by the ITF impact the state of the Pacific and Indian Ocean, as well as the air-sea exchange. So that's why the ITF play an important role in transporting mass, heat, and balancing water volume between 2 oceans of the Pacific and Indian Ocean. And the Indonesian seas is well known as the global epicenter of the marine biodiversity in terms of the coral, mangrove, and also seagrasses. Maintenance of the diversity of ecosystem and the productivity therein must be balanced by adequate nourishment supply. And for the coral reef, in this ecosystem is increasingly threatened by the ocean warming and also ocean acidification, calcification, and also dissolution of marine calcifying organism in this region is modulated by the carbonate system. So that's why we do research in this important region. And for the mangrove and also seagrasses is important for the blue carbon and its sequestration, and also for the carbon dioxide removal. And how about the inside Indonesian seas? Western part and eastern part is very quite different. Western part is shallow, while deeper in eastern part consists of the seal and also a narrow passage. The seal and narrow passage at the inflow and outflow are restricted water exchange between two ocean basins. Fresh water discharge with the large amount of the carbon and nutrient from the numerous rivers in Sumatra, Kalimantan, and also Java, and seasonal upwelling will with enriched carbon and nutrient in this region. However, scarce data coverage of the carbonate system in Indonesian seas. Previous studies only focus on the air-sea interaction. In general, their findings show a source of the CO2 to the atmosphere. However, vertical and horizontal distribution of the carbonate system and its transport associated with the ITF are unknown. So for the global scientific question and framework, how do physical and biochemical processes control the dynamic of the carbonate system in Indonesian seas? And we divide into two sub research. The first one is dynamic of the carbonate system in the western Indonesian seas during the southeast monsoon. And the second one is the transport and transformation of the carbonate system along the main route of the Indonesian truth flow. And we go to the second part. The western Indonesian seas is connected between South China Sea and also in the Indian Ocean through the Karimata Strait and also Sunda Strait. The region is characterized by the shallow water depth and significant river discharge from the major island. Seasonally reverse surface water flow driven by the monsoonal system. For example, during the winter time or December, January, February, water from the South China Sea going to the Java Sea. However, it is oppositely during the summertime, June until August, the water from the Java Sea going to the South China Sea and also intrude to the Indian Ocean through the Sunda Strait. And for this region, scientific question to be addressed is, one, what are characteristics of the carbonate system in horizontal distribution and vertical profile? What is the controlling mechanism of the carbonate system during water mass mixing? And the last one is how to quantify the effect of the water mixing on significantly biological mediated DIC. And to answer this scientific question, we established a sampling station to Western Indonesian seas, including Karimata Strait, Western Java Sea, and Sunda Strait. We carry out a cruise during early southeast monsoon with major parameter of the physical and carbonate parameters. Also, we normalize carbonate parameters during open ocean salinity of the 35 PSO. River discharge data were collected from the 6 rivers in the Kalimantan, Sumatra, and also Java, and showing lower discharge during the present survey, and it has seasonal variation. The largest discharge is recorded from the Kapuas River that may affect changes in the physical and biochemical properties in the Karimata Strait. And for the water mass mixing, in the upper 40 meters, water mass mixing between the Java Sea water, the Kavos River plume, and also waters from the South China Sea below 40 meters, additionally with the subsurface Indian Ocean water. And if we can see the surface distribution, salinity, DIC, alkalinity, and pH were low due to the Kapuas River plume, while the Western Java Sea and Sunda Strait, their distribution were homogeneous. For the vertical profile, y-axis is depth and x-axis is the transect line from here to here, from here to here, from to here to here. In the Karimata Strait, lower salinity, DIC, and alkalinity due to the impact of the Kapuas River plume, and in the Java Sea, homogeneous distribution, and in the Sunda Strait, lower value in the top of the 40 meters due to the intrusion of the Java Sea water, while higher value from the subsurface Indian Ocean water. And we compare NDIC in the Western Indonesian seas in the station 21 in the Sunda Strait with the Indian Ocean, South China Sea, and also Sulu Sea. And the result indicate that we found the higher NDIC compared to the other region, suggesting organic remineralization responsible for the higher NDIC in the top of the 100 meter of the Sunda Strait. However, normalized alkalinity, we can see in here a slightly constant, suggesting no observable difference in normalized alkalinity, mainly controlled by the mixing. For the overview of the carbonate system during water mass mixing, the DIC and alkalinity relationship can be used to identify typical water mass mixing. We found that two mixing groups were built, and the DIC each group may vary seasonally. From the alkalinity and DIC along the salinity gradient, we can see here and alkalinity was invariable against salinity, while NDIC was only variable in the Sunda Strait. And for the alkalinity and salinity relationship has a good relationship, while some data of the DIC are below the mixing line, suggesting biological alteration of the DIC. However, in all regions in the Western Sundas, Western Indonesian Sea is the CO2 outgassing to the atmosphere. How about the mixing in the shallow region of the Karimata Strait and the Sunda Strait? In the upper 30 meter, in the Karimata Strait, we can see in here the low salinity DIC alkaline is flow going to the South China Sea, while the higher value of DIC and alkalinity going to the Java Sea. In the Sunda Strait, we can see in here all the parameter salinity, pH, DIC, alkalinity, and also NDIC is slightly homogeneous in the upper 40 meters and slightly increase of the value due to the intrusion the Indian Ocean water to the Sunda Strait. We plot the DFS diagram, the slope of the normalized alkalinity and also NDIC relationship to diagnose the various processes that affect the of the carbonate system. We found that the Karimata Strait and Western Java Sea is mixed control air sea gas exchange and calcium carbonate precipitation and dissolution, while in the Sunda Strait is a biological alteration of the DIC. In the specific region in the Sunda Strait, We also found a strong biological alteration of the DIC. A good positive linear relationship between alkalinity and salinity indicate that waters in the surface mixed layer depths originated from the mixing between rainwater and waters beneath the surface mixed layer. Normalized alkalinity is invariable along salinity gradient, also point the present rainwater and member with the zero solute. Then the conservative mixing induced DIC and alkalinity value can be calculated using this equation. Delta DIC is the difference between the DIC conservative and minus the DIC measurement. If the value of the delta DIC is positive, it means the removal of the DIC, while the negative value of delta DIC, the addition of the DIC. We calculate DIC remove in the surface mixed layer of the Sunda Strait, followed by the super saturated dissolved oxygen. Along with the DIC removal, DO enhancement and also pH and omega were increased, with would potentially counter the effect of the ocean acidification via invasion of the anthropogenic CO2. And for the summary of Western Indonesian Sea, the first, the Kapuas River plume lower salinity, DIC alkalinity in the Karimata Strait, while the distribution of the physical and carbonate parameter in Western Java Sea and Sunda Strait were homogeneous. Second, the Tachanat Sea truth flow and subsurface Indian Ocean waters brought higher DIC and alkalinity to the Western Indonesian seas. And the last one, physical processes and air-sea gas exchange exert predominant controls on the carbonate system in Karimata Strait and Western Java Sea, while biological activity removed the DIC in the upper layer of the Sunda Strait. Let's move the third part of this presentation. And we know that the Pacific water going to the from the Pacific to the Indian Ocean through the Indonesian seas, we know the Indonesian truth flow, and then the pathway of the ITF is the first one is the main in the western route and also the eastern route, and then about the 15 spare drop water is flowing from the ITF to the Indian Ocean. However, we can see here the TS diagram slightly different between the Pacific and also all the region in Indonesian seas. And how about the biological material in Indonesian Sea would be transfer follow the transformation of the Pacific water. And if we can see in here in the surface along the density 21, we can see in here nutrient and nitrate, phosphate, and also silicate slightly lower. And then, however, in the surface density 24, we can see in here the nutrient is slightly lower in the Western Pacific, but slightly higher in the Indonesian seas and also in the Indian Ocean. It's mean a strong signal of the biological transformation within the Indonesian seas. And for the scientific question to be addressed, what is the general pattern of the carbonate system and how are they transformed along the main route of the ITF, and how much carbon is transported along the main route of the ITF? And then the sampling region we took during the October 2015 during the El Nino, and also September, October 2017 during the spurious IOD. And then the parameter is similar to the Western Indonesian seas. And then for the caveat during the study, such a combination provide a more comprehensive picture of the main route of the ITF, while the carbonate system data are in its scarcity in the region. Meanwhile, we are fully aware of the distinction between the two sampling events and examine how the sampling lag would impact our data interpretation in the carbonate system. And if we can see in here, during the two cruises, the North and South Pacific water are transformed within the Indonesian seas, and the ITF water in the Indian Ocean has unique properties compared to its origin in the Pacific water. And if we can see from the horizontal distribution, surface DIC, alkalinity, and DIC have similar pattern with the salinity, while the surface pH omega have similar pattern with the temperature. If we can see in here, the carbonate parameters, the low value in the main inflow compared to the outflow of passage of the ITF. For the vertical distribution, saline water in the upper 50 meters of Makassar and Lombok Strait, then that in the Mindanao, Sulawesi. And then we can see in here intrusion of the North Pacific subtropical water. However, in the eastern route, we can see in here for the temperature is slightly homogeneous in the upper 50 meters. And then we can see in here there is any intrusion of the South Pacific subtropical water in the Halmahera Sea, and then a slightly intrusion of the North Pacific intermediate water in the Maluku Sea. And we calculated the acid transport flux through the ITF passage, and then we found that the largest flux, about the 60%, is located in the upper 300 meters of the Makassar Strait. And then we calculated net carbon flux about the 51 millimole meter square per day, with the surface area of the Indonesian seas is about the 0.88. And then we divide the layer to calculate how about the flux flowing along the each passage, and then we can see in here there is any imbalance between the main inflow and also main outflow should be filled by the thermocline upwelling. However, in the different layer, there is any inflow will join with the deep overflow upwelling to the Banda Sea. We also use the isopic mixing model to calculating the mixing ratio contribute by the different water mass along the isopecnal plane. And then we want to know how about the contribution of the Western Pacific to the Indonesian seas. For example, for the carbon and also for the nutrient. And then we choose two end members are typically composed of the North Pacific water. We can see in here in the Mindanao current, part of the Mindanao current in here, and also the Indonesian seas in the Lombok Strait, proper water were selected. And then we can see in here for the Mindanao fraction in the Sulawesi Sea slightly higher compared to the Makassar Strait, and also for the fraction of the Mindanao current, the ice is slightly higher in the Sulawesi Sea compared to the Makassar Strait, suggesting the typical value or the typical of the concentration carbonate parameter slightly similar with the Sulawesi Sea, but slightly different along the Makassar Strait until the Lombok Strait. For the integration of the IC each station, we can see in here the value of the integration of the DIC is slightly lower in the Sulawesi Sea compared to the Sulawesi, suggesting there is any regional process that affect of the carbon in the Indonesian seas, so that the minimal DIC supply from the Western Pacific. We can see in here, we plot the DIC measurement and also DIC model, suggesting close to the line 1 by 1. However, some data is outside disaligned, suggesting biological uptake or some utilize of the carbon. And if we plotting between the fraction, median of fraction, and also the IC inventory, we can see in here, while the fraction close to the 1, indicating the influence of the Western Pacific is so strong, but the inventory is slightly higher. We can see in here higher the IC inventory in the Makassar Strait, Lombok Strait, with the fraction lower than the 0.5. And we plot in here the salinity, the IC, pH along the neutral density 21, 24, and 26. We can see in here strong transformation is located along the neutral density 24. For example, from here, it's like different for the IC and pH. And we can see in here, if the North Pacific subtropical water is slightly eroded in Indonesian seas along this neutral density. So it's mean the carbonate system also transform along, follow or in line with the ITF water transformation. And for the border implication, we can see in here the ITF has a direct connection to an inflow from the heart of marine diversity. And then the ITF is one of the major source of the carbon and nutrient to the Indian Ocean. And it flow with the South Equator Calien and is carried by eddies. And the ITF carbon flux is large enough to support the Indian Ocean primary productivity, and the net commodity production associated with the ITF is slightly higher than in equatorial in Indonesia, Indian Ocean. And the Indonesian Sea serve to fertilize the NP ratio of the Indian Ocean thermocline water, while higher silicate from the ITF is injected to the Indian Ocean intermediate water. This for the summary, the ITF subtank transformation is in line with the formation of transport the ITF water. Carbonate parameter have higher value in the outflow than inflow phasage. Upwelling from the thermocline layer and air CO2 exchange induced by heating of this upwell water are needed to balance the DIC budget. And the ITF carries a net DIC flux of 51 millimole per meter per day, with the largest portion in the thermocline water. This most increase in the IC occur in the upper 300 meter. And for the future work in this region, since we know from the previous presenter, the increased atmospheric CO2, and for example, from the pre-industrial is 280 ppm, and currently on August 2020 is 417 ppm. And then for the future works, we know that the Indonesian is the richest with the marine calcifying organism. And then how about the role of the Indonesian seas? Whether facilitating or mitigating of the ocean acidification. So that's why it is important to this region, even for the we know for the ocean warming currently impacted for the coral reef ecosystem. And for the conclusion, this presentation, water mass mixing dominated the dynamic of carbonate system in Western Indonesian seas during the southeast monsoon. Physical processes and air-sea gas exchange exert predominant control on carbonate system in the Karimata Strait and Western Java Sea, while biological activity removes the IC in the surface mixed layer and subsurface water of the Sunda Strait. Carbonate parameter have higher value in the main outflow passage than that in the inflow passage, And we know that the ITF carries net deacid flux with a largest portion in the thermocline water. Because of the limited observation data in terms of the both spatial and temporal coverage, the present study can only be seen as a starting point toward a comprehensive and holistic understanding of the biogeochemistry of the Indonesian seas. Maybe I stop in here. Thanks for your attention.
Thank you, Dr. Faisal. Interesting and insightful topic and many interesting points as well. Due to we are behind the time schedule, we decided to move to next speaker. If anyone has any question, please feel free to type in the chat box and Dr. Faisal will handle. And next talk will be Asian dust deposition into the Sunda shell region by Professor Rahim Mohammed. And let me briefly introduce Dr. Rahim Mohammed. He is currently a professor at Universiti Kebangsaan. He received his PhD at Hokkaido University, and currently he is the head of marine science program, and he was a director of ECOMAR, Marine Ecosystem Research Center. And his expertise include marine radiochemistry, coral paleoclimatology, marine geochemical balance, radioactive dating, and marine chemistry, marine pollution. Please, Dr. Mohammed. Floor is yours. You're still muted. Oh.
Okay, you see my slide?
Yep.
Okay, thank you, Chairman, and also thank you, the organizer, inviting me to give a simple talks, and also to thank Professor Talib, and also colleague in Xiamen University, and also the other university in China. So, and also thank also to my student here. So today I will try to share the idea. Before this, I saw to the candidate or to the presentation is about from Professor Bala is about acidification, and Dr. Faisal about carbonate. That's a very good and interesting topic. So, but anyway, for this floor, I will try to explain. It's a different topic. It's related on natural radionuclide in Sunda shelf, especially in atmosphere, sediment, and so on. So I go further. Okay, so in outline we will put introduction. So after that I will go to the transboundary pollutants. For example, in atmosphere is a haze, ash and dust, burning, and so on. So in the water column, the ballast water, current, and so on. So after that we go, we try to explain the radionuclide, man-made, artificial, and also is a natural radionuclide. After that, in the radionuclide, we have a short half radionuclide and long half-life. And scientific clues, some of the information what we have before long time ago, and also after that I will try to discuss what I mean some important point, for example, for the uranium-thorium series, Remark, and acknowledgement, and let's member. So for your member information, so colleagues at the moment in my lab, I'm from UKM. So mostly we have we organize about 4 projects currently. For number 1 is promote the pollution in harbor on seaport, or say instead of some state of Johor center like that. And also we have also a marine biodiversity study with a marine park, and transboundary pollutant. As for example, I put here is hazard, haze, ballast water, ash and dust, and so on, with collaboration with various universities in local and also in international universities. For example, from Ocean University of China, Tokyo University, and also the other agency, for example, Xinjiang University, and so on. So the last part is more on sedimentation rate, what I mean sedimentation, or more on the geochronology. So it's collaboration with FIO, Tonji, and so on. So that is about the 4 topic or 4 project at the moment we handle in my lab. So we go further. So we have 2 monsoon here. Is north is monsoon and then south is monsoon. So of course, for example, in Malaysia waters, we have a north is monsoon about the October to December, or sometime to January the following year. So, and the opposite one is southwest monsoon is about May until to August, something like that one. So that means 2 characters of the monsoon here. Okay. So, and the problem during that monsoon here, we have 2 characters of the problem here, especially in our EEZ water, or in our coastal water. Is, for example, is dust problem, as during north is monsoon, and the other one is southwest monsoon is the haze. So this example for the dust monsoon during what I mean the north is monsoon, dust deposition during the north is monsoon. That means example is 2002 is reported by Chinese scientists. So this is reported by Chinese scientists. They have various kind of what I mean deposition of the dust to the South China Sea. So this is example of the deposition of the during calcium during the event. So that's one also is by Thai 2013 is it? So that means a lot of iron. So that means so recorded is reported by their colleague. So the other problem is appear or happen in Malaysia in the southern South China Sea is the haze. So we have a country, we have a neighboring here is Indonesia, Malaysia, Singapore, Thailand, and so on. So the problem is haze. So that means haze usually is what I mean the cause of this forest burning or biological burning is appear in Sumatra or in Kalimantan. So that means we can see here the example I put here. So that means during the haze, what I mean a lot of the chemical, a lot of the haze. What I mean during the burning, a lot of haze transport from the main source to the deposit to the southern South China Sea in EEZ or Malaysia water. So that, and also there's some example here. So that's the haze is smoke. I put here as an example. And also we have also what I mean the agreement between transboundary haze pollution agreement between this Asian country and Asian country. So we have also agreement to control the haze, especially in Malaysia waters. Okay, so and these are 2 sources of the pollutant here. So that means I go to further is what radionuclide here. So we have 2 types of radionuclide. One is I put here is example of the artificial radionuclide. What I mean they discharge from the reactor nuclear. For example, the important here was 137 cesium, and so the other radionuclide we deposit into the ocean. This is one example. Okay, the other one is uranium thorium series. What I mean, this is a natural one. Before this is artificial. It's very very small activities or very low dose usually. but for for this kind of the uranium-thorium decay series is always is a natural. For example, it's important for this morning. What I try to see to highlight is lead to 10 here, and also polonium. We have also the other radionuclide is important for the marine study. For example, uranium-238, uranium-234, and thorium-234 here, thorium-230, and radium-226, radon, bismuth also here. So that means it's a kind of uranium series, 238 series. We have also 235 series. It's also important for the other purpose of the term of reference for here. For example, titanium also is usually we use for the to establish the chronology of the sediment, for example. So and so also we have thorium 232 series. Okay, so for example, it is important for the 228 radium or thorium 22 radium 228 and also thorium 228 also is usually used in a marine study. Okay. So that during the transport of radionuclide, for example, from the continental, for example, during the haze event, during the biological burning, or during the I mean the dust, transport from the northern during the northeast monsoon or southeast monsoon, they bring a lot of particles and they deposit to the ocean. This is, for example, I put example here, like, for example, lead to 10 or polonium to 10. Okay, so this is a two scenario. So from that, we try to establish various kind of expedition. So I try to put here the latest expedition we have. WRF-chem, FIO. Close over there 2018, 2019. Before this, like 3 years ago, before 2 years. Before. So and also we have various kind of expedition in coastal water, and also before the ESP is with various scientists from the various university here. So and also we have also the previous expedition. From the expedition, sorry. From the expedition, we collect various kind of sample. For example, for this case, we collect PM10 for the purpose of for this presentation. We try to explain this after this. And then also we collect also the others. There's a sample, for example, for the ecology, but I am chemist, so that means we also collect core as one. So this is a PM10, and also we have also collect water to see the other radionuclide in water column and so on. So this is color reef, the sample or color. We also estimate the age of the color. So and we bring to the lab this example. For here is example in the lab. So here is my student before, and also we separate and we analyze, and after we counting the nuclide. So we go to I try to quickly. So this is some of the result. Some of the information we got during the EPSP in 2009. 2009 here. Okay, so that means when we see the southern, we try to divide here southern South China Sea, Sulu, and Sulawesi. So that means south. The content of lead to 10, so polonium in seawater. So seawater. So that means it fluctuated. From stress situation. Either in southern China Sea or Sulu Sea. So that means the content is different from station to station. Okay, so and that means for that one, so we see that there's a correlation between content of lead to 10 and also the polonium. Well, before this, when we see here in the slide, if you here, so that means this lead at least is polonium and it's bismuth, and also that means it's like a family, is one of family here. So that's a parent, this is a parent, it's a daughter, that one. So that means it's an equilibrium between parent and daughter, that one. Okay, so that means that means slightly 0.6 square. So both of the radionuclide. So we also have what I mean in water column we during the course we also collect sample in various layer of the deck. So the content of the polonium slightly high compare lead to 10 here, but because of the limited of the sample, so we analyze some surface sample and for up to the 200 meters here is slightly that one. So this and also this station that one also, and this is a Sulu Sulawesi, this Sulawesi, the Sulu Sea. So that means the ratio with both of the nuclide about range about 5 to 6 or 7 about that. So then we see that the fluctuation also we also collect before the sample. We have a sample of the air sample, PM10 sample. So we also see the content of what I mean polonium and lead-210 in various sample various month, or for example here the January, from January to December the following years. So the content of lead-210 is total lead-210 is fluctuated, you see here. So then and also is polonium. Okay, so we try to relate the event after this. Okay, we see we try to relate with the event. Okay, so and we also try to analyze some sample in a coal power station. Before we have sample in offshore, and now we try to have a sample in coal power station. What I mean, like onshore sample. So during the experiment, we analyzed 3 elements over there. 3 nuclide is the lead-210, bismuth is in half-life about 5 days here. So and also also we have polonium here, the half-life about 3 months, and half-life for the lead-210 about 22 years. And we surprised most of the radionuclide is appear high in fly ash. Sorry, in all in Malaysia, but I collect from my student. So in fly ash, compare with the raw of the coal. For example, coal about less than 1, but about double or triple time in the fly ash. And also and also here is ground ash also is less about that one. So okay. So that means most of the radionuclide is attached in a particle during the during the burning, that one. For example, as I said before, in forest burning, a lot of radionuclide in a particle in transport, and also during when dust transportation for the northern part also have a lot of particle, a lot of the natural radionuclide, not only for that one. So not only for the natural radionuclide, we also have iron. Of course, we have a result of iron. Before this, we see the scientists from China also estimate that a lot of iron. So they need together, that one is iron of the one of the the carrier of the natural radionuclide. So okay, we go further. So that means we also try to see how the relationship between both of the place. I mean in suspended particle and also in liquid, that one. So we see most of the radionuclide is like a proportion. So here, what I mean clear here, bismuth, lead-210 also, and also the polonium also. Okay, that one. Okay, and after that we see the content of the the various month. Also we have also sample during the near the coal power station. We have a sample. Various month here. So for example, we have a lot of the average of rainfall. So a lot of rainfall in October, yeah, October. And at the same time we have a lot of deposition. Dust here. Fly ash here, deposit here. So that okay. Okay, so we go further, and it's here some of the, we see the content of lead-210 and polonium in various fraction of digestion. Here, for example, a fraction of more organic, we have also still have a lot, we have polonium here, lead-210 here, and also polonium here. Say the polonium in a fraction of iron, manganese, we have a sequential digestion. So that one here, and in the various month. So that means also for residual, we still have polonium here, and also the lead, so the lead. So that's kind. So that means we can see the most of the some of the lead-210 and also still attached with a detriter fraction. Okay, so that one. Okay, so this is the total. Of course, the total between before we digest, we make a fraction as one. So and also the various month and the content. When for example December, we have a lot of rain here. We still have a lot of lead-210 in sample of PM10 here. Okay. Okay. So this is before this. I repeat that one. So that means the content of surface of the lead-210, polonium lead-210, both ocean here is slightly similar. And also we also calculate the residence time. Most of the residence time, how long they stay in the water column. For example, here lead-210 is station, various station here. So the average about here about for the lead about less than 100 days here. Okay, and also the polonium about less than 150 days in the average. So 100 so that one. So that one. So and we try to see more clear what happened during the monsoon here. We know there's a monsoon here. So we have sample in onshore, in east coast of the Peninsula of Malaysia. Facing to the previous sampling area. We sampled before this in southern South China Sea, about here. So we have a sample on the shore here, for example, in Kota Baharu, in northern part. We have middle of the Peninsula of Malaysia. We have a Kuantan here, and also we have a sample in the Mersing is like near our marine ecosystem center. This is called Ikoma over there. So we also collect here rainwater here. So that means from the January to December, and we see here here is the up here is temperature. So and down here is blue here is rainfall that we see here during the December. Of course, a lot of rainfall for the station in that one. This content and here is Mersing. So then for the northern part slightly less during that one. So that means in Malaysia we sometimes we have a fluctuated of the raining event. For example, because we know that the northern part is slightly more related to north monsoon, and the southern part is likely is most affected by southwest monsoon. Okay, we have also collect for this case. We collect PM10. So at the one, so we see the content of PM10 is also different for the three location. For northern part, northern, middle, and the southern is different. We see here. And also both of that as I said before, there's both of that. Why the different? Because of the monsoon season. Is the northern part is more slightly related to the northern monsoon and southern is southwest monsoon. So after that we calculate or we try to analyze just let to 10 here. Just let to 10 because we let to 10 is more on is related what I mean what I mean a stable lead here. So the content of lead here slightly on the June is about 400, and here is about 400. Here the highest about 400, about 450, and here his highest about 200. The difference you see the difference. I will say this like this June here. June here is like March, and also this like bottom is like is March, April, or something like July, something. This is like that's why in Malaysia also in the East Coast we have a various time frame of the rainfall, and also we have the various time frame of the dust deposition. So that means also we content of pollen lead to 10 also we see here is different. So from that we see here the real question, and we put here. So from the January for of course different. We see here slightly the content of pollen lead to 10 is increasing during the early year, and slightly most the three station here, and the end of the year is slightly decreasing of the content. Is I think is more related to the content of the rainfall here. Okay, so that one. So we also try to see what happened during I mean the April. Most of we put example in April. So that means, as I say here, is become aware the source of the lead to 10 here. So here, so, okay.
2 minutes, please, Professor.
Okay, wait, I try to hurry. Okay, so that means I also try making a correlation between rainfall here and also temperature. So here example, and that's why so we put here so the correlation between two parameters we lead to 10 and rainfall and temperature. Okay, so this is like summary of that one, and also before I close here, so summarize the deposition of what I mean lactotan or the polonium in the southern South China Sea, especially in Indonesia, water is most related what the type or what the content of the source of the north is monsoon or south is monsoon. I put here. So after that, in the water column is more on biological process inside. So that means I put one simple one because the Strait of Malacca here is like it's closed system. I put here. And southern South China Sea is a semi-closed system, but we have what I mean Western Pacific Ocean and also the northern South China Sea over there. Okay, so that before I close, so I put a remark here. That means the porous marine and also the effluent of the atmosphere also, and also that one. So before I close, so I also thank to the Universiti Kebangsaan Malaysia, MOSTI, and FIO, and also Xiamen, also my student, helped me. So that and so here is currently in my student in my lab. Is working under me now. So from that, thank you. So any question I try to answer.
Thank you, Professor Rahim. We decided to move on due to the time behind.
Thank you.
So if anyone has any question, please feel free to try in the chat box, please.
Okay, thank you. Welcome.
And next speaker is Chan Maha. He's going to talk about ocean acidification and coral growth. Dr. Tran Manha from Institute of Marine Environment and Resources, Vietnam. Please. And Professor Lahim, could you bring your slide down and you would see it. Oh, all right. Are you able to share your screen? Yeah. Oh, we can hear you. I think.
Can you hear me?
Yep.
Okay. So thank you, Chairman Dr. Tachanat, and so thank you for Xiamen University and SOLAS project for held the online workshop. And I just show some preliminary result on the effect of ocean acidification on the growth of coral in the north of Vietnam under laboratory experiment. My name is Minhan. I'm working in Institute of Marine Environment Resources. It belongs to Vietnam Academic of Science and Technology. I'm a biologist, not a chemist. So I just give some result on the effect of OA on the coral. Due to the time very strict, and Professor Bala have already talked on known and unknown of OA. So I give very quick on the OA and move to the my results. But we know the burning of fossil fuel and destruction of forests is caused high of partial CO2 and level of CO2 to the atmosphere, and it's decrease PS. And ocean have observed a large amount of carbon dioxide, so we can see the illustration. CO2 higher and PS going down. Over the past decade, there have been many studies focused on potential impact on ocean acidification. However, the research regarding this issue remain very few, very scarce in Vietnam. And recently, our study present very briefly on acidification in coral reef, but only try to give a very basic data on the OA related to coral in Vietnam. We try to focus on the coral in the north of Vietnam here, and because it connecting Hanoi, Hải Phòng, and Quảng Ninh, it's an industrial triangle. So many human activity effect on the coral, but we try to eliminate. From more than 160 species of coral, we try to pick up 4 species for experiment. It's including massive coral, Poritet lutea and Gracia fasciculata, Cuniopora columna, and one branch, Acropora puncta. We select those species because they're very common, easy to see in the north of Vietnam coastal area, and specimen collected by diving gear and keep cool before sending to the lab. When go to lab, we set up the incubator for experiment. We put the light time. We simulate the natural light time from 6 a.m. to the 6 p.m. and light off from 6 p.m. to next day. And coral were kept in both tanks for 1 week with no impact to allow the coral to acclimate the laboratory environment, because when we pick up from nature habitat, they have some stress, so we need to keep them for acclimate. when coral, we observe when coral adapt to new environment with some tentacle begin to catching prey or moving normally, and we start the experiment. And coral will set control tank with natural pH about 8.1, and for experiment set by 7.8 with the same high RCP scenario. And after 4 weeks of the screening experiment, we see the aquaporon very sensitive to environment in the experiment tank, and it death begin second week. At for the massive coral like Porotet, we still going normally during the experiment, but the morphology is short tentacle physiology feature difficult to recognize, so we did not choose for next further experiment. And for glacier coral, with normally normally physical so well developed during the experiment for after 4 weeks, and gonioporan also, but gonioporan more common than in glacier, so we choose the gonioporan columna for species of experiment. And we do the same with the experiment screening. We collect again only focus on Goniopora columna to prepare for away experiment, and we tag them and put in the incubator and let keep for 1 week for acclimate the new environment. And for the setup, the environment parameter such as light, temperature, and dissolved oxygen will keep stable, and pH will adjust by change of partial pressure of CO2 beyond the IPCC low and medium and high scenario, and pH will lock using pH electrodes and calibrate every half day. And by using this system, the tank of control maintain 8.1, almost 8.2, and the experiment tank, treatment tank remain from 7.8 and drop to 7.5 to 7.6. We adjust a drop of CO2 to the incubator. And in addition, for monitoring the environment parameter, will assess every 2 to 3 days by filtration for calculating the total alkalinity, and using saturation by CO2 system. And we choose the 3 pH threshold, like low, medium, and high RCP scenario of IPCC. And total duration of experiment 34 days. And during the experiment, monitor the physical of coron like polyp contraction, the prey capture rate, and for the data will be recorded for further analyze. Oh, sorry, this is not my final dry. We measure the coron grow by buoyant weight by here Jokian. We measure the density of coron, density of seawater, and density of skeleton coron. And after 34 days, the real reasons so that the control incubator in the normal condition, it kept normal and grew rapidly from day 1 to 7. In the following week, chronicin well developed. Sorry, and the coron developed weight according to the equation. And after experiment, the individual coron still well developed. The for experiment from scenario ICP low scenario, the coron for 7 days, the coron developed normally and the tentacle healthy. The tentacle morphology were normal and the catching activity normal. And for ICP middle PS range from 7.7 to 7.75 for 8 days. Coron still normally grow. But for ICP scenario 4.5 is a high scenario. We less than 19 days, and from this 17 days experiment, coron grow slower. The physical of coron slower. The color fade and physiology activity catching prey is lower than previous, and they graduate death from the 27 to 23 and 27 days. Coron become die. You can see it. Summary of physical activity. We see the coron still normal in control incubator, and they decrease after we decrease PS. And the reason of monitoring the mass coron, we can see the growth decrease during the day, during the time. And we observe the structure of coron with scanning SEM, but at this time we do not see no significant difference compared to control and experiment structure of skeleton when conducting the reduce in PS condition. And we also with high definition of surface of coron skeleton, we could not see any different. And what trying to examine by X-rays structure, but we also could not see any difficult, any signature. However, when we analyze the weight of coron when cultivating coron in low pH condition, the density of coron skeleton change after control and normal. We check by Brusson-Wallace test. For after 35 days of experiment, we can see that from skeleton we have not significant consistent with the result of Foster when evaluate the influence of temperature combined with the high CO2. But we can calculate the growth rate of Bunipora coron about 1.05 centimeter per year. We follow the previous research where growth rate in 0.1 to 1.3 milligram per month.
1 minute, please.
Yes, and we can see some coron under normal condition. We try to according to the equation, but in low pH we have the minor of equation. So it's a time strict agenda. So if it is the first time we try to do experiment on a set of ocean acidification on coron. So if you have any comment or question, please give me a message. So I will try to reply. Thank you, Chairman.
Oh, thank you. Interesting point. And let's move on to the next invited speaker, Professor Iskandar, on the topic of dynamic of Indo-Pacific climate modes and impact on forest fires. Let me briefly introduce Dr. Iskandar. And Dr. Iskandar is professor in physical oceanography at Sriwijaya University, South Sumatra, Indonesia. He received PhD in physical oceanography from University of Tokyo. He was a JSPS postdoc fellow, NOAA research fellow, director of Green Research Center, dean of Faculty of Science, and he also served as a lead author of IPCC AR6 Working Group 1, Chapter 11, Weather and Climate Extreme Event in a Warming Climate. And currently he is a director of Higher Education Service Institute, Ministry of Education, Culture, Research and Technology, Republic of Indonesia for Southern Sumatra region. His current research focuses on ocean and climate variability in the Indo-Pacific region, in particular detecting Indo-Pacific climate modes, and so Indian Ocean dipole and impact on rainfall. And of course, he published more than 70 peer-reviewed journals. So please, Professor Iskandar.
Thank you, Tachanat, for the time. So please let me share my slide. Can you see my slide?
Yep.
Okay, thank you. So I am Ishak Iskandar from University of Sriwijaya in South Sumatra, and the title of my presentation today is about the impact of Indo-Pacific climate mode and their impact on, dynamic of Indo-Pacific climate mode and their impact on the forest fire in Indonesia. So this work is done with my colleagues, Dr. Mardiansyah, Dr. Irfan, and Dr. Lestari. And Dr. Lestari is previously was my student. Is now she's working at the Institute of Technology of Sumatra. So this is the organization of my talk. So I start with the motivation why we do this study, and the data we use to explore the dynamics of Indo-Pacific climate mode, in particular the Indian Ocean dipole in 2019 as the example, and we will show the impact on the Indonesia and related to the forest fire. Actually, this is not a forest, this is a peatland fire. And we try to show you the correlation between the number of hotspots and the level of the groundwater. And the final one is the summary. So I would like to start from this slide, which show you the climate driver for Indonesia. So Indonesia is located between Pacific and an Indian Ocean, also between the Asian continents and Australian continent. So the Indonesian is vulnerable for the extreme climate event in the Indo-Pacific region. At least there are 5 climate drivers in Indonesia. The first one is a diurnal cycle. This is in daily time scale. And then the second one is the Madden-Julian oscillation. So this is the ocean atmosphere interaction within intraseasonal time scale. It's originated from the tropical Indian Ocean and then move eastward across the maritime continent, the Indonesian continents, until the Pacific Ocean. And the second one, because it's located between the ASEAN and Australian continent, so it's affected by the monsoon system. So the Asia-Australian monsoon system within in seasonal time scale. And the fourth one is the climate mode originated from the Indian Ocean. We call it as Indian Ocean dipole. And this within a biennial time scale. And the fifth one is the ENSO, the climate mode originated from tropical Pacific Ocean within the interannual time scale. So there's 5 climate driver for Indonesia, which make Indonesian climate very dynamic. And this show you how the Indian Ocean dipole affecting the Indonesian region. So the upper panel show you the normal condition or the negative IOD condition. So during the negative IOD condition, the SST around the Indonesian is a little bit higher than normal condition, and the wind is blowing from the west to the east. We have a westerly wind, and then so that the thermocline in the eastern part is deeper than the western part is shallow. And the active atmospheric convection is occurring in the above of the high SST, so that the rainfall is normal during the normal condition, or even surface during the negative Indian Ocean dipole. But for this positive IOD condition, the situation is reverse. So we have a southeasterly wind, which bring the warm pool from the western moving, shifting to the center or the western part of the Indian Ocean, so that the convection also moving westward. So the Indonesia has less rainfall or negative anomaly of rainfall. And the IOD influence precipitation in Indonesia during boreal summer and fall. So from June, July, August, September, October, November. And it's because these develop in spring usually, and peak or mature in the fall and decay in winter. So when the positive IOD occur, so it's during the dry season in region in July, August, September. So it's because the severe drought in Indonesia. And for the El Nino and La Nina, so it's almost similar with the IOD, but it is originated from the Pacific Ocean. So when the El Nino comes, so the atmospheric pressure in the east is fall, and then the west is rises, so that the wind is blowing to the east, cause the easterly or the trade wind is weakened or even reverse direction. So we have a sinking air in the west, so it's a dry air in the west, and then a warm, cool, and moist air is in the eastern part, so that the convection is occurring in the eastern part of the Central Pacific Ocean. So during the El Nino, we have less rainfall, and it's occurring in the during boreal fall and during boreal winter. So from September until February the next year. The La Nina condition is a reverse condition, opposite situation is occurring during La Nina. So we have La Nina, we have more rainfall in Indonesia. So this is the brief description of the IOD and El Nino effect on Indonesian precipitation. So we can see that this is the composite of the rainfall during June, July, August, and during September, October, November for the positive IOD, and the right-hand side for negative IOD. So we can see that during the positive IOD, we have a deficit rainfall from June, July, August until September, October, November, and peak is in September, October, November. But during a negative IOD, the peak of the rainfall is not in September, October, November, but in June, July, August. Because during June, July, August, we have a dry condition, but with the negative IOD, it's become a wet condition in Indonesia. So we're going to focus on this positive IOD in 2019. This is the similar one with, but for the ENSO, for the El Nino and La Nina event. So the left side for the El Nino, the right hand side for La Nina. So you can see that during the El Nino, especially in September, October, November, we have very dry condition in Indonesia, a severe drought occurring in Indonesia. But during La Nina, we have a high rainfall, as in negative IOD, the highest rainfall is occurring in June, July, August. So what's happening in 2019? So we have smokes from forest or pit fire covering the southern part of the Sumatra, including the Palembang city in South Sumatra. And it is more than 3 months we have this kind of experience. So the left side is the firefighters trying to conducting the forest, to fight with the fires in the forest. And this is from helicopter, and this is the flight radars showing that the flight cannot landing in Palembang due to the smoke. So they try to make a flight like this, but they cannot landing in Palembang. And the right side is the elephant. So you can see that the elephants and the surrounding is the smokes from the forest fire. So this situation is occurring almost 3 months from July, August, and September. So then we try to evaluate how this smoke fire is coming from IOD 2019. And we conduct multiple statistical analysis using available data, precipitation, sea surface temperature, wind, and other satellite and weather analysis data. So we use this data, and here is the evolution of the Indian Ocean dipole in 2019. So the above figure showing the dipole mode index, showing, and the green curve is the eastern pole, and the the western pole, and then the red curve is for the eastern pole. So the dipole mode index is eastern pole minus western pole. So we have this index. The positive mean positive Indian Ocean dipole, and negative means negative Indian Ocean dipole. And we can see that the positive event is occurring from July and then decay in fall in December. So we have a very strong Indian Ocean, positive Indian Ocean dipole in 2019. And if we look at the Nino index to see the ENSO evolution, we cannot see any significant value for the index. All Nino 3, Nino 4, 3.4, 1 point plus 2 index did not show the evolution of El Nino or La Nina. And it's mean that in 2019, the positive IOD event that influenced the rainfall in Indonesia only. See, this is the spatial evolution. So from May, June, July until December. So the peak of the event is in September, October, November, when the dipole of the SST anomaly established. So we can see we have negative SST in the eastern part, and then warm or positive SST anomaly in the western part, and it's a combined is followed by this one easterly wind anomaly. So this easterly create the upwelling in the eastern part, and then make the SST become cooler in the eastern part, the positive feedback. And if we look at the wave dynamics, so this is the let's say this is the sea surface high, the shading indicating the sea surface high, and then the vector indicate the surface current. So we can see that we have upwelling already here, and this showing by the negative sea surface high and in the eastern part. And if we look at when the wind is established in September, and the surface current also indicate the westward anomaly, and this easterly wind create the downwelling of Rossby wave off equator, and then upwelling Kelvin wave along the equator. So this downwelling Rossby wave move westward, and then when it's reached the western boundary, it's reflected back to the east along the equator as a downwelling Kelvin wave. On the other hand, this upwelling Kelvin wave move eastward. When it's reached the eastern boundary in the Sumatra, it is reflected back to the internal Indian Ocean as upwelling Rossby wave. You can see this one and this one, and Kelvin wave is like that. So the evolution of the positive Indian Ocean dipole shows wave dynamics occurring in the tropical Indian Ocean during this event. And also we note that we cannot observe the fall wind jet. Usually we have a strong eastward jet along the equator during a boreal fall in September, October, November. But because we have positive IOD and the wind is easterly, it's caused the opposite current in the surface, and we do not have fall wind jet during this period. And if we look at the Walker circulation, we can see that the above the cold SST anomaly, we have a downward motion here in the Eastern Indian Ocean, and we have upward motion in the Western Indian Ocean. So downward motion it means the dry air, and the upward motion is moist air, so that the eastern part, the Indonesian region, experience deficit rainfall, whereas the Western Indian Ocean, Africa and India has surface rainfall. And we can see this from this one, so it's the precipitation. Now, what is the impact? So the impact is because we have a very dry condition, we observe a hot spot from August until September. You can see this, there is weekly hotspot, so density distribution of the weekly hotspot. So the red means extremely high. We have a lot of hotspot during this. So and it is mostly observed in the pit area. So the yellowish here mean pit area. So we observe it more in the pit area. And if we look at the hotspot density from 3 events in 2006, 15, and 2019, we found that 2019 is the second largest after extreme El Nino in 2015. And this is the density and this is the distribution, and mostly occurring in the pit area. Here is the pit area here. And to show the dynamics, why the hotspot occurring during this dry season, it is not only due to the deficit rainfall, but also there are another parameter that cause the hotspot is more denser in the pit area. So we use the data, temperature, rainfall, groundwater level, and soil moisture observed by Xiamen station. Xiamen is sensory data transmission services assisted by Midori Engineering Laboratory. So this is the ground station measuring these parameter: temperature, rainfall, groundwater level, and soil moisture. And we use 4 stations here, 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 and it's located near the pit area. This is the result. So we can see that the blue is the rainfall. The blue is the groundwater level, and the green is the yellowish is the rainfall. So when we have a rainfall, the groundwater level is increasing, but when the rainfall is deficit, and then the groundwater level is decreasing. So the decrease of rainfall caused the decrease of the groundwater level, and there is a short intermittence of the increase and decrease of groundwater level due to the precipitation. So we can see that if we have high precipitation, and then groundwater level is decreasing. And if we look at the relation between groundwater level and the hotspot, we can see this one. So when the groundwater level is decreasing, the hotspot number, the number of hotspots is increasing. So from here, we can make a proxy. So the groundwater level can be a proxy for the hotspot. In a certain level, the hotspot is appears. So what is the critical value for this one? The critical value of the groundwater level is about 0.5 meters. So once the groundwater level is above 0.5 meter, I mean is the negative 0.5 meter, and the hotspot will appear. So it's very important to maintain the level of the groundwater to keep the pit is wet, so that the hotspot cannot appear in this area. So this is the main finding of this research. So this is the summary. So I think I close here for any question. Thank you.
Thank you, Professor Iskandar. Very interesting talk. Before moving on, just quick question. So we finally consider Indian Ocean Dipole as biennial due to basin resonance between Rossby and Kelvin wave.
Yes, theoretically, yeah, biennial, but sometimes it's established not only by dynamics of the ocean dynamics, but also the iris interaction. So they theoretically, due to this ocean dynamic, is occur biennially, but in fact, not only ocean dynamic, but also the iris interaction play a role to for the IOD to be occur.
Thank you. And last speaker for before lunch, we have.
Thank you.
Dr. Ahmad Fairuz from Malaysian Meteorological Department, Malaysia. So, please.
Hello, can you see my slide?
Yep.
Yeah, okay. So thank you, Dr. Moderator. So my voice is clear?
Yes, clear.
Yeah, okay, yeah, thank you. So thank you, Dr. Moderator. And then very good afternoon to all the participants. So for today, I will talk about the greenhouse gases measurement in Malaysia. So basically, we are not a researcher basically. So we are basically what we call the data provider, and also we are monitoring the greenhouse gases in Malaysia, basically. So yeah, so I have a very short presentation today. So let me start. Okay, so the slide is moved. Is it the slide is moving, right?
Yes, it's moved.
Yeah, okay, thank you. So basically in recent years, so basically the occurrence of extreme weather in Malaysia is increased. That's because normally people related it with the what we call the climate change, or what we call global warming. So basically we like to see whether this also related to the what we call the increase in greenhouse gases in the atmosphere. So basically in recent years, we have what we call the abnormal weather pattern is some sort like tropical depression that are causing the Peninsula Malaysia last year, and also what we call the abnormal wet condition over the Malaysia during the Southern Monsoon. That's abnormal, what we call abnormal weather pattern. That's we currently experience. Okay. So basically for the introduction, so basically Malaysia has been monitoring the atmospheric composition since 1976. And then we, of course, we have some sort like analysis to study about the effect of this atmospheric composition to the meteorology, such as the formation, transportation, and distribution of air pollution, which duly affect human life and environment. So currently we measured chemical composition of rainwater such as pH, anion, cation, conductivity and heavy metal, aerosol concentration such as PM10 and PM2.5, of course aerosol, ozone, UV radiation, greenhouse gases, and reactive gas concentration. Okay. So basically we set up our station based from the what we call the LabMO frameworks. The LabMO, World Meteorological Organization, through the Global Atmospheric Monitoring Program, normally established to conduct the observation of CO2, methane, nitrous oxide, and CF6 through the GOA station network. Basically, we have Danau Valley Station since 2003, and basically we have installed, set up other 3 stations in 2022. So this is basically the instrument that we use in the Lembah Danau in Sabah. So basically we have what we call the tower with the height more than 100 meters. And then we also have a few types of instruments such as here we use the Picaro, and then of course the LICO. And then we also have the automatic flash sampling to measure all the parameters. So currently we have changed our Picasso with the ADR instrument. Okay. So basically this how the setup of our station. So basically we have the tower height more than around 100 meters. So we have 4 towers. So basically one tower in Sabah, and the height is around 100 meters. In Sarawak is around 106 meters, and the rest 2 in the Peninsula is around 60 meters. So basically we install our station or tower in the peak of the mountain. So basically our station is located above from the 1,500 meters from the mean sea level. So basically it's above from our planetary boundary layer. All right. So this is the rest of the 3 stations. So it's in Sarawak, in Cameron Highland, and also in Langkawi. So we set up this station in 2022. So basically this is some data. So basically this one is from the Lembah Danam. So right. So sorry. Okay. So basically the red cycle is there from the flash sampling, and this the continuous observation is from the analyzer. So basically we can see that since 2010, so basically the CO2 concentration in Malaysia is roughly around 390 ppm, increased to around 412 ppm in 2020. All right. And then from the latest concentration in Malaysia in July 2020, so basically as we expected, there's what we call during the southern monsoon, basically Malaysia experienced what we call lower than average global average CO2. So basically it's shown by the over the Sabah and Pahang area. So basically the global average is around 418.9. So basically in our Sabah is around 413, and Cameron Island is 417. So for the Langkawi it's more than 419. So this I think we need to see why this thing happened over the Langkawi. So for the methane, so basically as we expect that in general Malaysia experience more what we call the methane concentration based from the what we call the agriculture activity that's occurred surrounding our station. Right. So this is the comparison between our in Lembah Danam and Mauna Loa in Hawaii. So basically we have since 2010 we have what we call consistent observation with the Mauna Loa, except for the methane which show higher reading in Dana Valley. This atmospheric methane abundance probably due to intensive agriculture activity in local regions surrounding the Dana Valley. All right. So this is our monthly greenhouse gases at Lembah Danam. So basically we experience what we call the higher GHG during the northeast monsoon or boreal winter. So basically it's consistent with what we call the strength of the northerly wind, because during this season we are we are prevailing by the what we call northerly or northeasterly wind. So this suggests that the transboundary origin of the greenhouse gases is come from the north. All right. So here is we compare our Dana Valley station with the Western Pacific Ocean. So basically we make the Western Pacific Ocean as our reference. So we want to see whether there is what we call the origin of the greenhouse gases, and also whether there's what we call the carbon, whether it's anthropogenic or non-anthropogenic source. Okay, so basically what we can see here that for the CO2, so basically in what we call for the Dana Valley, so basically it's in general is lower than the during the Tanang Valley, and then for the data carbon 13, so basically it's in the opposite direction. So what we can suggest here that basically the increase of the carbon 12, so it means that maybe it's there is some influence of the what we call the anthropogenic carbon from the what we call after this origin from the not of region. So after this we can see that the origin of the carbon. All right. So beside that, we can see that for the N2O and SF6, so this consistent with the CO2 pattern. So roughly we can say that the GHG is the origin from the north. So okay, here is more clear. So basically we can see that where the CO2 is increased, the carbon 13 is decreased. And then also when the carbon CO2 is increased, so there is a same pattern where N2O and roughly N4CH6. Okay, so yeah, so basically this show us that the possibility of the origin of the GHG comes from the north, and then of course the possible of the non-local anthropogenic carbon. Yep. So basically in near future we expect the anthropogenic GHG in Malaysia expected to further increase. Thus we expecting the increase of temperature and rainfall amount in Malaysia. So basically in Malaysia, so for about 30 years we have seen the increase of 0.1 to 0.6 degrees Celsius for that 30 years. So and then we expect with the increased trend of the greenhouse gases, so we also expect that the temperature in the Malaysia will be also increased. Okay, so for my summary, in near future, anthropogenic GHG is expected to further increase. They're expecting the increase of temperature and rainfall amount in Malaysia. So the second one is the CO2 increase when northerly winds are predominant and decrease during dominant or southerly and southwesterly wind. And the third one, when we compare with the what we call the Western Pacific Ocean, so basically we expect the potential of establishing of non-local attenuated sources of CO2, N2O, and F6. And the last one is the potential of establishing a localized anthropogenic sources of this methane. So with that, thank you. Back to you, Dr. Moderator. Yep.
Thank you, Dr. Ahmad.
Yep.
We may have like a room for one question if anyone want to ask. How about diurnal variability?
Yeah. So yeah. So because yeah, basically for the diurnal we have we see that GHG is increased around 8 o'clock, 9 o'clock is the local time, and then decrease in the afternoon. So it's consistent with the respiration and the photosynthesis, basically. Yeah.
All right, thank you everyone, and let's give a big round of applause to all speakers this morning.
Yeah, thank you.
Thank you.
Yep.
And we're gonna have like a 1 hour lunch break, right, Lily?
Yes, exactly. And we're sorry for the delay. So please come back at 2 Malaysia time.
Yeah, good. All right. Okay, maybe you can start now. Very good afternoon and good evening to everyone. My name is Yijun Tam. I'm from Sun Yat-sen University. And welcome everyone to this the second session of today's workshop, which focus on the SOLAS core team 4 and 5. So in these sessions, we have 6 presentations altogether. And the first presentation will be an invited presentations will be presented by Professor Punyaslok Baduri. And I will give a brief introduction to the Professor Punesh Lok. Okay, he completed his Master of Science from Edinburgh and PhD from Plymouth in United Kingdom. And subsequently, he did his postdoctoral research from Princeton University. He is currently a professor of biological sciences in IISER, Kolkata, and leads the Center for the Climate and Environmental Studies, as well as the Center for Excellence in Blue Economy. He is an editor of a number of leading international journals, including Piaget, Geoscience, Letters, Frontiers in Marine Sciences, and Ecological Solutions and Evidence. He is also co-chairs in the Regional Advisory Committee of the Asia-Oceania Geoscience Society, coordinator of the South Asia Regional Hubs on Ocean Acidifications, part of the writing team of the United Nations Law of the Sea, and a member of working groups of Global Soil Partnerships of the FOA. And Professor Punesh Lok presentation title is Microbially Mediated Biogeochemical Cycling in Coastal Northeast Bay of Bengal, linking aerosol influences with functional microbial goods. Yeah, Professor, to you.
Thank you so much, Professor Tam. Just let me try to share my screen. I hope all of you can see the full screen, maybe? Yeah. Yes, I think so.
Yes.
Great. Thank you so much. Thank you once again, and thanks to the organizers of the SOLAS Southeast Asia workshop for their kind invitation. And I'm very much looking forward to interacting with all of you when the meeting becomes physical and we're able to interact further. I'll be very briefly talking about today, sharing some of our thoughts and our ongoing work, what we have been doing in the Northeast Coastal Bay of Bengal, which is part of the Northern Indian Ocean, where we are trying to understand the implications of land atmospheric influences on the coastal ocean and linking those with critical processes such as carbon and nitrogen cycling, which have been mediated by microbial communities. So blue economy is a cornerstone of many countries globally, and global ocean play a very important role in sustaining the GDP of these countries. In particular, South Asia, Southeast Asia, and East Asia, many countries are largely dependent on the coastal ocean. And if you look at some of the statistics, for example, 1 in 10 livelihoods depends on fisheries, and it has been estimated that the ocean economy will reach by about $3 trillion by 2030. Not only that, many of the coastal countries which are surrounding the Bay of Bengal, they are particularly dependent on the fish proteins from coastal ocean. And it's more so because of the increasing population and the development that are taking place in this region. So there is more pressure on the coastal ocean. What we cannot ignore is the influence of the land atmosphere on the ocean. And I would also like to bring in one more partner or one more component, which is the freshwater. So land, freshwater, atmosphere are interacting with the ocean, and therefore these are having huge consequences in terms of controlling the flux rates of different types of elements, and ultimately affecting the global climatic patterns as well as the regional climatic patterns, which again influences many of the livelihood that happens in Asia, particularly agriculture. If we look at this work of Zheng et al. 2020, which is published in Nature Climate Change, you see that the global sulfur dioxide emission actually has changed dramatically. Actually, it's on the decrease, and that is because of tough legislations which are put in place in many countries globally, Europe or in parts of North America, and also in Asia. But if you look at the organic carbon and the black carbon, that has been increasing. So therefore, there are effects of organic carbon, black carbon ultimately on the coastal ocean. And of course, in addition to sulfur dioxide, you have got nitrogen, forms of nitrogen, which is which can be transported from the land into the coastal ocean and can influence. So there is a possibility of nitrogen enrichment, and aerosol is not stable for a long period of time. It can have short stability, and of course, when you're looking at the coastal ocean can be a source for aerosol formation. So the interaction is very, very complex, and many of these aerosols which are of anthropogenic origin, they seems to be influencing many of the processes that are taking place in the coastal ocean, and that might be also happening in the northern part of the Indian Ocean. And therefore, we need to look at these components holistically, and that's what the SOLAS program has been all about. And it's very important to understand how this works out in South Asia, Southeast Asia, and East Asia. And the reason is that coastal ocean are strongly influenced by the LOA interactions, and aerosol is a big component of the LOA interaction, particularly land boundary systems which have very high density of population. They will influence the aerosol and the types of aerosol, and ultimately that will have implications on food web and ecosystem services. Of course, many of these we actually do not know what their long-term and the short-term implications are, and then that ultimately will have huge consequences on the sustainability of the ocean. When we talk about ocean, we cannot think ocean just as an ocean, but we need to introduce the concept or need to understand it from a perspective of urban ocean. The land masses are becoming more urbanized, and there will be influences of LOA, and therefore the urban ocean has to be made sustainable, which will have consequences, for example, on fisheries, and ultimately that will affect the UN SDG goals that we all are aiming to achieve, both at the national level and at the international levels. What is more important or interesting to know is how this interaction really works out when you look at microbial loop. I mean, the microbial loop is very well characterized in oceanic system, but particularly if you look at the coastal ocean, say biotopes such as estuaries or mangroves or
Hello, Prof. Are you there?
It seems he lost the connection.
Yeah.
Yeah, that's it. For 0 minutes.
Yeah, maybe we should wait for a few minutes.
Yeah, he's
Hi,
back.
Prof. Yeah. You are muted. Can you please unmute? Yeah.
Yeah, sorry about that. That bit of hiccup that happened. I hope you can see the slide now. Yeah. Okay.
No. Can you share?
Okay.
Yeah. No.
Okay, just a minute. 1 second. Yeah, I think it should be fine now. Yeah.
Yes.
Yeah, sorry about that. So what I was saying is we look at diatoms, we look at bacterioplankton, we look at marine planktonic cyanobacteria, and we try to assign these groups in terms of functional guilds. That means what is their importance in terms of specific function in coastal ocean, and how these functions are shaped by aerosol influences. So we work in one of the world's largest contiguous mangrove ecosystems, actually the world's largest contiguous mangrove ecosystem, the Sundarbans. It is located in the northeast part of the Bay of Bengal. And here I've put a graphical representation. So the Sundarban is very strongly influenced by Kolkata. This is a very big megapolis, and it has the third highest density of population per square kilometers. And you have got the big river Ganga, which is flowing into the Sundarbans. So in the Sundarbans, the freshwater flow can vary between 42,000 cubic meter per second to 120,000 cubic meter per second during the monsoon. And the suspended particulate matter can vary between 200 to 800 milligram per liter. So it's really very murky water that we are looking at, but it's extremely productive, very rich in coastal fisheries. But there is also strong influence of the aerosol from the land coming down and influencing this mangrove. This is also a UNESCO World Heritage Site and a Ramsar site. So this has got a huge socio-economic cultural significance globally. In Sundarbans, we have set up a time series. So it's down south of the western part of Sundarbans. This box place is where our time series site is. This site was established in 2010, and we have been taking ecological snapshots, physical chemical snapshots, including some aerosol snapshots, trying to understand how this ecosystem is changing in course of time. And here is one example where you can see how the oscillations in salinity has been changing over last 10 years. And actually, this part of the Sundarbans, the western part of the Sundarbans, has become more saline in the last 10 years than it was before, partly due to diminishing flow of the fresh water. And that has got huge consequences, because when there is a change in fresh water, but also you have more aerosol deposition happening, the stressors, net stressors become more and more stronger. Here, what we look at is a carbonate chemistry of the coastal ocean. And in the inaugural lecture, we heard from the speaker from Singapore talking about ocean acidification. And essentially, we are looking at the carbonate chemistry to understand the ocean acidification, and we want to try to link it up with the land and the atmospheric influences. So here, we look at how at a seasonal scale the carbonate chemistry parameter changes in terms of total alkalinity, in terms of salinity, dissolved oxygen, and pH. And when you look at the carbonate chemistry data, for example, total alkalinity and plot it against salinity, there is some relationship, but the relationship is not very robust. The reason for that is the significant influence of the fresh water that is coming down in the system. What we also see is that the PCO2 values actually show quite a bit of variability, and they show a very strong seasonal change or seasonal attributes. Ultimately, what happens is this system becomes a transformation from a sink into a source. So summertime it becomes a source, and rest of the year it is a sink. So it generates methane during the summertime, and then that has got influences on the aerosol formation that might be taking place in the region. But we must not forget the aerosol that is coming from the megapolis, the urban influences of the aerosol. So we are trying to understand how this part of the Northern Indian Ocean is changing. And not only that, we are trying to link it up with the other regional seas and oceans in South Asia and beyond South Asia. And that has led to the establishment of the South Asia Regional Hub on Ocean Acidification, where all the countries of South Asia and beyond South Asia have come together to use a standardized protocol for measurement of carbonate chemistry of the ocean to understand how the ocean is changing, because that is very important ultimately to link up with the land atmospheric processes. And this entire program is supported and endorsed by the Global Ocean Acidification Observing Network, the International Atomic Energy Agency, UNESCO, and of course my institute, Indian Institute of Science Education Research, Kolkata. So this component also builds up to our lower measurements and trying to understand what is really going on in terms of the changes in the functional guilds of microbial communities. I quickly go and show you some of the guild attributes that we see in this area. For example, here is one plot of the bacterioplankton communities from the Sundarbans versus Columbia and Delaware Estuary in North America, and Geelong Estuary, Pearl Estuary, and Hangzhou Estuary in China. We have selected these three estuaries in China because these have mangroves in it, And of course, our Sundarban has many estuaries. They also have mangroves, and of course, these ones don't have mangroves. So, but there are a lot of similarities in terms of the aerosols attributes of the signals, in terms of the physicochemical gradients that are there in the surface ozone. And we see that in Sundarbans, the forms of carbon actually shaping the functional gills in members of Firmicutes and Bacteroidetes, which are very, very unique. And these are having resulting consequences for ecological stoichiometry and ultimately functioning of the ecosystem. So we did not know, or we had no idea, what is the aerosol influence on these gills that we are seeing, that is unique signatures that we are encountering at the microbial level. When we take the bacterioplankton and go into autotrophic photosynthetic organisms such as light-driven, of course, marine planktonic cyanobacteria, we also see that this region also has unique population of marine planktonic cyanobacteria, and they show a spatiotemporal variability that is controlled seasonally, of course. And this system is dominated by populations of Cyanococcus. And it seems these Cyanococcus have developed or evolved to produce unique microbial gills. We have compared these Cyanococcus signals with other regions of the world, for example, the Monterey Bay, the South China Sea, and the Baltic Sea. And what we see is that the Sundarbans and in South China Sea, there are some clades are there. There are functional gills, which are essentially these clades. They have similarity in terms of metabolic pathways, but there are also some functional gills such as the clades which are mentioned here, SCB1, SCB2, SCB3, which are very, very unique. They are found in Sundarbans and in Baltic Sea, so very localized habitat, but also there are some groups which are exclusive to Sundarbans and only found out here. So the question that came to our mind is, what is the influence of this of LOA? So for example, aerosols or the land influences, how they're interacting with these gills that we are observing. And that led us to actually try to see, can we grow these organisms under laboratory condition? Can we sequence these organisms and try to gather the information which can probably tell us about the aerosol influences? So here is one example I'll give you, where we have established culture of Cyanococcus murigangai. It is a new species of marine planktonic cyanobacteria. We see that this organism can withstand nitrate up to 550 micromole. And this is quite unusual. Usually in this kind of system, to have 50 micromole nitrate coming down just from the land influences will not be happening, number one. Number two, the stoichiometry is very different. And we think this nitrate is not just the land-driven nitrate. There are some aerosol influences are there. So we started to sequence the genome of this organism. And to our surprise, what we found out was this organism has unique signatures of iron binding proteins. And these binding proteins that they have, these are not been reported in other Cyanococcus, coastal Cyanococcus at least previously. And we believe this is because in this coastal water, iron is quite abundant. But actually what is happening is iron is present in complexes because there are a lot of organic molecules out there. So ligands, essentially organic ligands. And one quick way of getting the iron is from the aerosols, So we think that these aerosol influences actually is providing iron some way or other, and that is influencing the influence this organism to develop or to come up with different types of ferritin-like proteins or that can bind to iron. Siderophore groups are also there. Not only that, we found the catalytic subunit of formate dehydrogenase, which is linked to the DMSO superfamily. So there is signature which indicates that this Cyanococcus ultimately has some influences on DMSO. This is something which has not been reported very widely in the group Cyanococcaceae in cyanobacteria. It has been reported in another group of cyanobacteria before. So that is something which is very unusual, and we believe that these are all influences of the aerosol. I'll give you another example where we have also identified and isolated and established a culture of a diatom, Thalassiosella sundarbana. It is a new species. When we sequenced the genome, we found that it has got an extensive biosynthesis pathway for dimethyl sulfonneopropionate. And that is something which is very unusual in addition to many other isoforms of carbonic anhydrase and superoxide dismutase. Not only that, it has got extensive nitrogen and Fe acquisition pathways, what we also found in the Synechococcus. So we believe these are signatures that are strongly influenced by the aerosol deposition that is coming down from the Kolkata megapolis or from the surrounding areas. Now the question is, how do you quantify them? Of course, one way of quantifying the influence of this land-ocean atmosphere interaction is eddy covariance, flux tower, where you can measure the eddy covariance or measure the GHG influences. And of course, airflow can be imagined as a horizontal flow of numerous rotating eddies. Although this diagram looks very chaotic, but believe me, these components can be measured from the tower. But of course, this tower has to be tall tower to measure so that we can figure out the non-anthropogenic signals from the anthropogenic signals. So both kind of towers should be very, very important. Luckily, we have one tower which is out here in the Sundarbans, and this is also part of our seasonal time series site. We have in addition to our weekly time series, which I mentioned before. And we see in our seasonal time series site, there are really episodic patterns of nitrogen that is only happening during certain times of the year. When? During the post-monsoon time, particularly end of November to February, where the air current are actually slowing down because of the changes in that air temperature, because the winter season is in force. And it seems there is a localized effect of the aerosol deposition that is happening when the concentration of the ammonia and the nitrate in the systems becomes higher. Not only that, we have got anticyclonic eddies that are also in play, which means they are transporting this aerosol from one place to another place within this mangrove. When we are talking about huge area, almost 3,000 square kilometer area, and that seems to be having an effect on the unique microbial communities that might be appearing and disappearing only during these winter months in this mangrove system. So this is definitely something which is driven by availability of nutrient, and aerosol seems to be an important factor. We also see an interesting trend, which is that there is an increasing nutrient enrichment which is happening in the Northeast Bay of Bengal. And this is typically anthropogenic nitrogen, because we have done isotopic measurements to see that. And we believe there is a very strong influence of the aerosol that is happening over the years, which means the nitrogen in the water, coastal water of Bay of Bengal is increasing. And that will have huge shift in terms of the socioeconomics of the region. That brings down very quickly that I want to show you a couple of some very quick measurement data. Here you can see two measurements. Just for an example, I'm showing. You have got PM 2.5 measurement for the month of November, one of the dates of November, and one of the dates of December of the same year. And you can clearly see that the PM 2.5 value changes dramatically. In December, these values become more and more significant compared to what it is in November. That means this aerosol transport actually is influenced as the temperature becomes lesser and lesser. When we take this aerosol measurement and go down a little bit in the Northwest Bay of Bengal, here we are doing some measurement again in another site, which is Chilka Lagoon, Asia's largest lagoon, which is also a Ramsar site. Here you see in December the trends, again a daily trend. You see that the aerosol values actually changes with the progress of time and day, and of course there is an influence of the temperature. So this will have deposition, short-term deposition of the aerosol, and that will influence the microbial functional guilds, and ultimately that will control the process. And of course, this is an ongoing study at the moment where we are looking at the microbial communities that are there in the aerosol, and hopefully in the next meeting we'll be able to share the data. Besides that, we have also taken the flux flux tower data, eddy covariance data, and with collaborators in IIT Bombay in India, we are also trying to calculate the net ecosystem exchange. And we see that the net ecosystem exchange in the Sundarbans mangrove actually changes dramatically during the winter months, and it seems that there is a strong influence of aerosol. So what does it really mean overall from a blue economy viewpoint? Well, if more and more aerosol deposition is going to happen, there is going to be a temporarily positive influence, but actually long term there's going to be a negative influence, which means it will have implications on fisheries, on biodiversity, on waste management, and ultimately it in itself is deteriorating air quality, also is part of the disaster and management in a changing climate. And that will have ultimately the sustainability of the ocean. So when you look at the challenges of the coastal ocean, we need to look at the scale of interaction between land, ocean, atmosphere. We cannot omit out the aerosol component, so that we can understand what are the short-term and long-term impacts. And to be able to do that, we have to invest, and big programs like SOLAS are very important, because the science that come out of it helps us to understand what is really going on in regional seas and ocean. And we have to innovate how we can actually minimize these risks. Why do we need to do that? Because ultimately these aerosol deposition, which are of anthropogenic origin, which we have enough evidence by now, will lead to increase the chances of harmful algal bloom. And ultimately that will lead a scenario called jellyfish bloom. And ultimately we are looking at urban ocean, which will lead to gelatinous ocean. So there are a lot of short-term and long-term implications of this in terms of the aerosol deposition. So overall, where do we go from here? Well, we have to address the SDG goal 14, which is a sustainable blue economy. And of course, biodiversity contribution to GDP is very, very important. Therefore, we have, when you look at ocean pollution, we cannot omit out role of aerosol deposition. And when you look at aerosol deposition, we can look at the components more intrinsically, and that is very important, because ultimately we can create opportunities to tackle the SDGs by innovation, and ultimately back way we can go back and make our oceans healthy and contribute to the sustainable blue economy. And that is the basis of the second World Ocean Assessment Report, which got published last year by the United Nations, where we says that climate change, particularly fishery dependent developing states, are extremely vulnerable, and we have to include the aerosol component in it. Thank you all very much for listening, and I'd be very happy to take any question or any introspection that you have. Thank you very much.
Okay, thank you, Prof. Priyaslov, for this interesting talk. Is there any questions from the floor? You can turn on your mic to ask, or you can type in the chat box if you want. Yeah, any questions? Any questions that related to that you want to ask? Yeah, yeah, Prof. Maybe I have some simple questions actually. Actually, I know very little on this microbial because I don't work on it, but it's quite interesting that you have linked this aerosol to this microbial influence on this microbial communities in the coastal area. From one of the slides, I think you measure the aerosols from this from land to ocean. Like, what is there any compositions that you measure? Any chemical compositions? What is the dominant chemical composition in those?
So we have been. Yeah, I think that's a very good question. Sorry to interrupt. We have been. Our focus has been mostly on nitrogen. So we have been only measuring the nitrogen isotopes.
Only nitrogen.
Yeah, we have been measuring the nitrogen isotopes. The reason is we believe that from the land, because these are very heavily urbanized areas, and therefore the aerosol will have more nitrogen fraction in it. And we wanted to see the natural nitrogen and the anthropogenic nitrogen, how that disparity in terms of the oceanic current, coastal ocean current, ultimately influences the yield. So to answer your question, we have only measured the nitrogen using isotope measurements, stable isotope measurements, and we know that which forms of nitrogen these are. And we see as you go more towards the boundary of the urban area, essentially the anthropogenic signals are more and more prominent, and the deposition rates are obviously probably prominent, because that's the reason why the communities, the microbial communities, they are able to adapt and grow in very high concentration of nitrogen.
Yeah. Yeah, very good. Thank you, Prof. So
Thank you so much.
Any other questions from the floor? If no, then yeah, thank you, Prof, for your presentations, and we'll move on to the second talk of these sessions. Okay, so the second invited presentations will be presented by Dr. Qi Li from Institute of Physical Chemistry, Roscasilano in Spain, Madrid, and currently he's in Hong Kong Polytechnic University. Okay, let me have a brief introductions for Dr. Qi Li. He obtained his Bachelor of Science in Environmental Science from Sun Yat-sen University in 2010, and Master of Science in Environmental Science from Peking University in 2013, and PhD in Environmental Engineering from the Hong Kong Polytechnic University in 2018. Dr. Li then worked as a postdoctoral researcher in the Spanish National Research Council, CSIC, from 2018 to 2022, before returning to Hong Kong Polytechnic as a research fellow recently. So Dr. Li's research lies in the multi-scale modeling of multi-phase processes involving the interaction between the atmosphere and the Earth's surface. Dr. Li's study addresses the underlying causes of regional air pollution and global climate change with a focus on the role of reactive halogen sources and chemistry in Earth system, providing evidence-based suggestions for formulating mitigation policies. And his presentation title is on reactive halogen species and their impacts on air pollutants in China's seas and Western Pacific, WRF-chem studies. Yeah, Dr. Qi, to you.
Okay, thanks, Tim, Dr. Tim, for the invitation. Can you hear me well?
Yes.
Okay, what about the screen? Can you see my screen?
Yes. Good.
Okay,
yes.
Okay, good, cool. Thanks for the invitation, I said, to share my research, and thanks to the committee for arranging the online workshop. My name is Cindy Lee. Like Jim said, I was a postdoc when I was doing this study. I was in Alfonso Saiz Lopez group in the Spanish National Research Council, and now I've returned to Hong Kong to as a research fellow. So today I'm going to present something about reactive halogen species and their impacts on air pollutants in China seas and Western Pacific. And mostly I use a regional model of WRF-chem to do these simulations and to assess the abundance of these species and their impacts. And most of the contents that I presented here today were already published on JGR. If you find it interesting, please have a look at it. My presentation is going to be divided by 4 parts. First, introduction, then method, then results and discussion, and the last one is conclusion. So as a very brief background is that we know that the shipment is very important and a dominant method for distributing, like moving the products from one place to another, or from one continent to another continent, and it's very critical in sustaining the world's economy. So and it has attracted quite a lot of attention in the past 2-3 decades that the air pollutant emitted from the shipment, including the primary emission and their secondary products like sulfate, like sulfur, nitrogen, and VOC species. And they have been reported to affect the atmospheric composition, coastal air quality, and even global climate and human health. In the meantime, the last 2-3 decades, I would say, the role of reactive halogen species. So here we define reactive halogen species as mostly the inorganic halogen species, but also some very short-lived halogen, organic halogens that has a lifetime less than 180 days. So which means that these species will have very active involvement in the atmospheric chemistry in the lower part of the troposphere. And this type of research has received quite some recognition and attention in the past 2-3 decades. And we know that the oceans are the largest contributors to these halogen species. However, there's very few quantification of the halogen impact on ship-originated air pollutants, and that's where I'm going to present today. So here are some key chemical reactions divided into 3 parts. The first part is halogen sources that, like I said, chlorine and bromine and iodine, they all have very dominant origins from the sea, from the oceans, either directly from seawater or the sea soil aerosol, which originate from the ocean. And the second part is the halogen impact on air pollutants, like maybe the most important chemical reaction in atmospheric chemistry is the halogen atom with the ozone that deplete stratospheric ozone, but this reaction also occurs in the lower part of the troposphere. And halogen also involves in the NOx chemistry, like XO, like reactions R7, XO with NO, or R8, XO with NO2 to form halogen nitrate. And the third part of the chemical reaction is the halogen impact on oxidants, including, there are like 10 reactions here, but there are 2 main direction of the halogen impact on oxidant is that when you are in a clean region, like in open ocean or in the free troposphere or in the stratosphere, that when you have halogen, that means halogen will destroy ozone and reduce the levels of all kinds of oxidants. However, if you move into the sort of like a polluted region, like coastal or along the shipment or continental area, from reaction R9 to reaction R11, we see that chlorine and bromine atom will react with the VOC species, and with the involvement of NOx, then the halogen chemistry will increase the level of atmospheric oxidants. And then the second part is the method. So this is a case study, so I'm going to put a little bit detail of the method that I use. So WRF-chem model, it's based on the 2005 original growth WRF-chem model. And then in 2019, Badia, one of my former colleagues, she implemented comprehensive reactive halogen sources and chemistry and applied in, let's see, in Southern America at that time to have it validated. And then in 2020, I used this model and implemented some sources of Hono and aerosol and ground surface, but that might not be very important here today, but yeah. And then later on, I used this model and then I applied it to China Seas and also the Western Pacific to look at the similar levels of halogens and their impacts. I used the data, including the ship emissions from EGA and air pollutants from MAKE and oceanic halogen, which is calculated online from Badia, and also fire emissions. This is a global data set. And I use an unset data set to drive the model, to constrain the model. The simulation setup, simulation were conducted for 1 month in the summer of 2018 with some spin up period. Okay, and then I conducted 2 scenarios, including one called no hal, which means no halogens. And that means no oceanic halogen emission, no halogen chemistry. And the other one is full case, including everything. And the difference between these 2 cases, then I call it the impact of halogen source and chemistry. Okay, then the third part is the results and discussion. So firstly, I show the ship, let's see. Okay, the ship emissions on the left here is the NOx emissions, and the middle is carbon monoxide and VOC, and the right is the SO2. And then we see very let's just say elevated emissions from the shipment in this part of area that would otherwise clean open ocean, but with these emissions here, you might see a different story. And on the left, there's a blue line over here that will be used for further cross-section analysis. That means like a vertical analysis. Okay, then here is the halogen abundance and the partitioning. On the left here, I show the similarity levels of halogens, including chlorine and bromine and iodine. So on average, domain average for chlorine it's more than 100 ppt, and for bromine it's about 2 ppt, and for iodine it's 8 ppt. Yeah, about 8 ppt here. So these levels are sort of high compared to like a remote area, partly because with the involvement of Xiamen that we actually induce more halogen release from the ocean surface and from the seashore aerosol. And then I look at the loading of these halogen species and their difference between the daytime and nighttime. And maybe you can see it's a little bit too small here. Like during the daytime, the chlorine is about 147, and during nighttime 135. For bromine, during daytime is about 2 ppt, and nighttime is 1.9. So basically, the loading of these halogens were quite similar between daytime and nighttime. However, the partitioning of different species showed very distinct patterns during daytime and nighttime. For instance, for chlorine, during the daytime, the dominant one is HOCl, but in the nighttime, according to our simulation, molecular chlorine could be even higher than the rest of the species. And for bromine, it's the same story, that during daytime, it's HOBr or bromine nitrate. But during the nighttime, it's BrCl. Similar for iodine, it's HOI versus the neonite and like iron-3, etc., etc. So with these elevated halogen species over these oceanic regions, but with Xiamen, here we show that on the left-hand side is the no health simulated levels of NO, NO2, and ozone. That means if there is no halogen in the system, what does the simulation look like? That's on the left. That's on the left. In the middle is the full case. That means we have considered halogen in this module already. And on the right is the relative changes. So basically, we see that with the consideration of halogens, the spatial pattern doesn't change much, except from the unknown. So we see the ship tracks, although after the consideration of halogens, the ship tracks is less evident, with an average reduction of about 20%, mostly because with the exo plus NO reactions. And for NO2, similarly, and the reduction is about 19%. And for ozone, it's about 70%. Here I show some of the chemical reactions if you're interested to see. And then we also look at the vertical, let's say the vertical profile of this halogen impact. And similarly, left is no halogen, middle is full, and on the right side are relative changes. And we see that halogen reduce both on NOx and ozone throughout the marine boundary layer. And even in the free troposphere, go up to about 1,000 meters above the sea level. So such halogen effect would affect the vertical transfer of air pollutants from the surface either from ship emissions or even from continental, like from, we can see from the left, from the west part. Okay, and it will affect the air pollutant transfer from the surface to the marine boundary layer and to the troposphere. And then we also have a look at the halogen impact on atmospheric oxidants, including OH and HO2 and NO3. And like I said, for oxidants, it seems the situation is more complicated. For OH, we see that on average, there are 16% of reduction. However, there are some grades like along the coast, or even like for HO2, we see that along the ship tracks, we see some enhancement after adding the halogen sources and chemistry, and we attribute this enhancement to the reactions initiated by the chlorine and bromine atom. Let me see. As we'll see, right? Yeah, and then you can see here R9, R10, and R11. That so that chlorine and bromine involves in the VOC oxidation, which takes part in the polluted area, that will increase the production of OH and SO2. So that we can see some enhancement over here. But for NO3 seems to be more homogeneous. That's because both ozone levels and also the NO2 levels, that both of them are the precursors of NO3 radicals. So we know that OH and HO2 are like daytime, we call them daytime oxidants, and they are involved in almost all the secondary air pollutants like ozone and sulfate and nitrate, aerosols and SOA formations, though, and during the daytime. But during the nighttime, it's the NO3 radical that will react with those precursors to form aerosols and secondary pollutants. Similarly, we take a look at the vertical profiles of OH and HO2 and also NO3. So for OH on the left, you see that if we don't consider halogens, the level is about 0.3, 0.5, 0.3 to 0.5 ppts below like 400 meters. But when we have the halogen chemistry, then it seems that most of them drop below 0.3. And on the right side, we can also see the of course the relative changes could run up to like about 400 meters and even much higher. And we also see that these notable influence can also be seen for HO2, even above like 400 meters or even 800 meters above. And for NO3, most of them are confined in the lower part of marine boundary. That's because NO3 requires both NO2 and ozone, and we know NO2 is mostly confined in the lower part from the Xiamen and from the continental sources. And like I said, the decreasing factor due to halogen is more intense and reaches to more than 1,000 meters because both NOx and ozone are significantly reduced. Okay, the last part is a very brief conclusion, some take-home messages. So the first one is that through our simulations, which was validated using a previous, or I forgot to show that, which was validated using previous observed levels of like a BRO and IO in this region, or similar regions. And then we see that through our simulations, the halogens have quite elevated levels in the lower troposphere in China Seas and then Western Pacific, and which require, like I said, require further measurement, that we call for further measurement in this region to to verify or to quantify the levels of these red halogens. And the second highlight is that we show that the halogen affect abundance, and more importantly, the distribution both horizontally and vertically of atmospheric oxidants and also the air pollutants over these oceanic regions. Although this is a case study, but we still, at least for this region, we call for like a consideration of the halogen impacts on ship original air pollutants when we consider or when we formulate the policies to improve the coastal air quality or even global climate. And if we move out of this case study region, which is China Seas and Western Pacific, like we go to North Sea or Southern Europe or Northern Europe or Northern Pacific, North Atlantic, where there are quite busy ship tracks, we would expect that similar or even more intense effect of halogens could be expected along those ship tracks. And when we consider the change the regulation of shipment emissions and the impact on coastal air quality and climate, we would recommend that halogen chemistry could be included or could be considered when we do that kind of assessment. So these are some acknowledgements for financial support and computational support by NCAR and model support by NOAA and the partners. Yeah, I think that will be all for my talk. Thanks again for the invitation, Jun. And yeah.
Okay, thank you, Dr. Chi. Yeah, a very good and interesting topic on this influence of ship emissions on the halogen chemistry. Is there any questions from the floor? Yeah, to Dr. Chi, whatever you want to ask or whatever you want to know from this research, please go ahead. Yeah. Any questions? Yeah, I hope there are some questions from the members. Yeah. Yeah. Any?
Hi, Jin.
Yeah.
I have one here.
Yeah. Yes.
So T, thank you very much for the the nice talk, for the excellent talk. So it seems there is a regulation, of the IMO on the sulfur concentration, right, from the ship emission. But how about halogens? Is there any relevant regulations already?
As far as I know, no, I don't think there's any regulation related to halogens, not just ship, not just co-bending, biomass, nothing. I don't think there's any specific regulations for halogens. That's one of the things that Jun and we have been working on recently. That we show that the halogen impact could be widespread, like in all kind of environment. We see halogen species and very elevated levels, but halogen is not like nitrogen or not like sulfur. Halogen could be two things. First, it could be a pollutant because it's part of the PM2.5. Like chloride could be part of it. And the second one is, more importantly, that halogens is also a source of oxidants. So like when you emit halogen along with nitrate, a lot of nitrogen and sulfate, so like halogen act as a pollutant, and that is as an oxidant to oxidize the other species, and all of them combine together to form pollutants. So yeah, I don't think there is any, but we are calling for such attentions. And then we hope that more people are working on this topic, and yeah, we could see the coming.
Yeah, so just let you know that there will be a relevant discussion session at the upcoming SOLAS Open Science Conference. So which takes place, end of September. So welcome.
Okay. Thanks.
Yeah, thank you, Lily, for the question. Yeah, actually, Dr. Chi, maybe he has introduced some of the importance of the halogens, and so maybe Chi, you can explain more a little bit. What is the importance of these halogens on the halogen species in the atmosphere to this to the members, so they have more, just a brief introduction. What is the importance compared to this more typical halogen species like the CFC stuff? What's that difference of this? Maybe you can explain again.
Yeah. Okay.
Yeah.
Thanks, Jim, for the suggestion. Yes. So when we talk about halogens, most people will think about the CFCs that destroy, that deplete stratosphere ozone in the South Pole during spring, and that's the most famous, I would say, the most famous topic of atmospheric chemistry, or even in the whole atmospheric science field. But then after, let's say, 1995, after or 2000, with the development of instruments and with more interest in embedded in this field, there have been quite widespread detection of what we call reactive halogen species, like I said, inorganic halogens and some very short-lived organic species with a lifetime lower than 180 days. That this species could have active participation in the atmospheric chemistry in the surface, or even marine boundary layer, or if there's carbonate, then you'll be in the continental boundary layer and in the free troposphere. That this halogen, let me show you okay, let me show you here. These chemical reactions that I showed here, like it has impacts on what we call ozone, which is a greenhouse gas, which is also an air pollutant. So it has both effects, like both increasing effect in the polluted region, and also it has depleting effect in the clean region. So like if you are in the polluted regions, then when ozone is already very high, then halogen will make it even worse. When you have halogen in the polluted, you have even higher ozone. But then if you are in a clean region, then you don't have much VOC and don't have much NOx, then halogen will destroy ozone. Okay, that's one thing. And the second part is that halogen also involves in the formation of secondary aerosols like sulfate, like nitrate, and SOA. That's because chlorine and bromine atoms mostly, they are involved in the VOC oxidations that will lead to the let's say production of OH and NO2 and even NO3. And if we look at the long-term greenhouse effect, that we also see the halogen could be taking part in methane chemistry. That's because methane has two dominant, let's say two dominant oxidants. One is OH and the other one is chlorine. Okay, so chlorine is already halogen, so that we know the halogen will affect methane. But on the other hand, halogens will affect the OH abundance, mostly increase OH in the polluted region, and the second one is to decrease OH in the clean region. That means halogen has like two direction of effects on OH, which will affect the methane oxidation rate in continental area, in the free troposphere, and then in the ocean region, and even in the Arctic. So the halogen impact on atmospheric chemistry is quite, let's say, quite widespread, but quite complicated. It really depends on each region's chemical mixture of VOC or NOx or even ozone levels, and even and these species. Then yeah, it's a very complicated system. I hope that answers your question, Jim.
Yeah, very detailed. I think. I hope every one of us can at least know the importance of this halogen in this and I think, is there any more questions from the floor related to this topic? If no, then maybe if you have further questions to Dr. Chi, you can just put it on the chat box, and then
yeah.
Okay. Yeah. So thank you very much to Dr. Chi. Yeah, thank you for your presentations.
Yeah, thanks.
Yeah. Thanks. Okay, maybe we move on to another speaker. Dr. Chi, can you unshare your So yes, the next speaker will be Dr. Fiona King from Institute of Oceans and Earth Sciences, University of Malaya. The presentation title is Emissions of Volatile Halocarbons from Tropical Marine Algae. Yeah, to you, Dr. Fiona.
Yeah, just a while, yeah. Okay. Is everything okay?
Yes, yes. Yeah, you may start.
Right. Good afternoon. My name is Fiona. Today, I would like to share our research at the University of Malaysia on the emission of volatile halocarbons from tropical marine algae with emphasis on the seaweeds. So just now, Dr. Chin Yi has delivered an interesting topic on halogens as well. So mine is more to the biogenic source, okay? And this research is led by Professor Siu Moi Pang, with members from our university as well as the University of East Anglia. So marine algae comprising of seaweeds and phytoplanktons, there are important coastal and oceanic sources of halocarbons. And these halocarbons, as Dr. Lee mentioned, they contribute to reactive halogens that will implicate the atmospheric chemistry, as well as destroying stratospheric ozone. And due to the lack of data, huge uncertainties exist in the predictions of this global halocarbon budget. And as a result of the phasing out of long-lived halocarbons under Montreal Protocol, the relative contributions of biogenic short-lived halogens to the stratosphere has increased. And currently, biogenic short-lived bromine contributes to around 25% of the total stratospheric bromine. And this relative contribution continue to increase. Also, the fact that the world seaweed cultivation has been increasing may likely aggravate the situation. Here is the statistics from the Food and Agriculture Organization, which shows the main seaweed producing countries in the world. Several Southeast Asia and East Asia countries contribute to a combined 97% of the world seaweed production. And also there's a rather high amount of seaweed produced by Southeast Asia countries like Indonesia, Philippines, and Malaysia. And this happens to be in a region with deep tropical convection that could carry these short-lived halocarbons into the upper troposphere and lower stratosphere. And in the recent years, there's a surge in interest in large-scale farming of the red seaweed Asparagopsis taxiformis due to its potential in reducing the greenhouse gas methane. The benefit of growing these seaweeds on a large scale to reduce methane actually is still up for debate. This is because the ability of these seaweeds to reduce the enteric methane in the ruminants like the cattle, it lies in its ability to produce large amounts of bromoform. And it's this bromoform that will help to reduce the methane. So here we can see that seaweed of the same genus, which is the Asparagopsis armata, has been recorded to be the highest emitter of bromoform to date. And collectively, the marine seaweeds are estimated to contribute to around 40 to 80% of global bromoform. And they also emit other compounds such as dibromomethane, dibromochloromethane, as well as diiodomethane. And these halocarbons are produced in the seaweeds from hydrogen peroxide through the activity of the enzyme known as haloperoxidases. And this could happen under normal metabolic changes to environmental factors such as light and temperature, and could also be elevated under stressful conditions. As the seaweeds can be found in various habitats with different environmental conditions, changes in the environmental factors such as irradiance, temperature, seawater pH, and so on could affect the halocarbon emission by the algae. Right now, the challenges in the estimation and prediction of halocarbon budget are often caused by the biological variability, spatial and temporal changes, and a lack of data input from biogenic sources. And these factors contribute to the huge uncertainties that exist. And in view of the global climate and environmental change, the expansion of seaweed industry, as well as the interaction between seaweed and the environment, it is therefore necessary to increase the data input from the tropics by profiling the halocarbon emission by selected marine algae from various habitats, and also to investigate the various environmental factors that could affect the emissions, and to determine the contribution of tropical marine algae towards the halocarbon budget. We have conducted several lab-based incubation studies to investigate the effect of several environmental factors, including irradiance and temperature on selected species of tropical algae. And with that, we found that irradiance, it promotes the halocarbon emission in selected tropical seaweeds. And from the left table, it shows positive correlation between irradiance and halocarbon emissions in one of the seaweed. However, the degree of correlation, it varies between these seaweed species. And this agrees well with the findings in temperate seaweeds, where there's a correlation, there's a pattern with that correlates with the changes in irradiance during the diurnal changes. Meanwhile, we have also managed to determine the emission rate of these four seaweed at seawater temperature, ranging between 20 to 40 degrees Celsius. From here, we can see that the emission rate of bromoform reaches up to 800 picomoles per gram seaweed per hour. And we also profiled the emission trend across the tested temperature at 5 degrees Celsius intervals, during which the effect of exposure duration was also tested. And we found that short-term temperature increase enhance the emission in one of the seaweed, while longer exposure period to temperature change shows negative correlations. And this could possibly be caused by the destruction of photosynthetic apparatus in the seaweed at high temperature. Besides lab-based incubation, we have also conducted field studies investigating the emission at various seaweed cultivation systems, namely the onshore tank, offshore platform system, as well as at the cage culture that we place at the river mouth in Kelantan, which is on the east coast of Peninsula Malaysia. So we have cultivated two commercially important seaweed, which are the Gracilaria and the Kappa ficus. For this, the seaweeds were grown at the various cultivation systems, and they were incubated in a chamber, and the air release were then collected and into a canister and then brought back to the lab for analysis. And the results showed that emission of bromoform by the different is affected by the different cultivation systems. The highest emission was from the cage culture of Gracilaria manilensis, which was placed at the river mouth. And this significantly higher results could be due to higher phosphate level, lower salinity, as well as a greater temperature fluctuation at the river mouth itself. And we have also found strong correlations between halocarbon emissions with irradiance and temperature at the farming sites. And by combining the emission data from the offshore platform, we are able to derive the average, lower bound, and upper bounds of the light to dark emission ratio for the two seaweeds. So on average, daylight emission by Gracilaria was around 13 to 16 times higher than the dark, while for Kappa ficus, it emits 3 to 6 times higher amount of halocarbon during daylight compared to the dark. And these ratios could be useful for estimation and prediction of diurnal emission from the seaweeds. Also, based on the emission rates from the same study, we took the bold step to extrapolate the emitted bromoform from the harvesting of carbophycus based on the seaweed production data that we got from the FAO report in year 2020. And this crude calculation gave an estimated rate of between 63 to 323 mole of bromine per hour that was emitted by the total seaweed produced in year 2020 itself during harvesting. And we have also estimated the total emission of bromoform during the farming of the 182,000 tons of carbophycus in Malaysia in year 2020 by considering the production capacity of the sea area and determining the total area used for farming in year 2020. We were able to estimate the flux rate per total farming area in the entire year, and subsequently the contribution of bromine by carbophycus during the entire farm period in year 2020. And the total contribution of bromine by the farm carbophycus in Malaysia in year 2020 was estimated to be between 15 to 102,000 moles of bromine, while the cover triangle, which include production from Malaysia, Indonesia, and the Philippines, they contribute to around 800 megamoles of bromine per year in 2020. And this is the comparison of the estimated bromine emitted by Malaysia and the curved triangle during farming and during harvesting in year 2020. However, these are very rough estimation derived from a small scale sampling data, and much remains to be done. So in summary, halocarbon emission by tropical seaweeds are much affected by changes in the environment, and farming activities could contribute to a large amount of bromine in the Southeast Asia region. The emission of bromoform is predicted to increase by up to 29% under the RCP 8.5 scenario. And therefore, in light of the rapid expansion of seaweed farming, there's a need to increase the baseline data by profiling and investigating the halocarbon emission from various habitats, including the locations where seaweeds are farmed, in order to refine the estimation and to better determine the contribution of farming activities towards the halocarbon budget. And this figure shows just how little research has been conducted in the field of algae-based halocarbon studies, especially in the Southeast Asia and East Asia regions. And therefore, we would like to take this opportunity to encourage prospective regional partnerships in this area of research. You are welcome to write to us if you would like to know more. And with that, thank you for your time.
Okay, thank you, Dr. Fiona. Any questions from the members of the floor to Dr. Fiona? Is there any questions or any specific topics that you want to understand more related to this talk? You can just ask. Yeah, maybe I will start with some, not a question. Actually, I'm very interested in Dr. Fiona's work. It's very important work as well, especially for this aquaculture or this seaweed culturing field. I have some questions. I think you did mention that there are difference of emissions rates from farming and harvesting, right? Yeah, if I'm not mistaken.
Yeah.
Yeah. So what causes this differences? And during the farming stage, is there also difference between these biological growth stages, like from how big the sizes to yeah? Is there any difference in rates in between this farming period in terms of these emissions of bromocarbon? Yeah.
The estimation was based on the final biomass that we got from FAO, which is the total amount produced per country per year. So yeah, we did not put into account the growth, the different stages of growth. But that's a good point. The difference between farming and harvesting here is that harvesting, the seaweeds are basically out of the water. When you're taking it out from the water, so the halocarbons will be in the air, so it's like a direct emission. While during farming, it's more in the seawater, under the water, so there's a flux that the flux rate that needs to be taken into consideration. Yeah.
I think this is important works for future works as well for estimating the fluxes and also the emissions rates, because these rates are very important to demonstrate modeler, especially how much rates they need to put into their models, as well as this for predictions. Yeah, and also maybe you can briefly tell us why they are like that. This seaweed actually they emit a lot of different halocarbons, right? Different types of halocarbons. Why they are why there is? Can you just explain very briefly why some halocarbons are higher than compared to the others? Yeah, is there any explanation for this?
Yeah,
like,
yeah,
like
it's
some
actually
chlorine species and bromine species. Yeah.
Yep, it actually also is related to the mechanism of production itself. Yeah. So the halocarbons are produced by haloperoxidase, and the type, the common type of haloperoxidase that present in seaweeds are the bromoperoxidases. So these bromoperoxidases, the dominant compound that produce the dominant halocarbon compound that they produce is bromoform. So that is why we get a larger amount of this halocarbon compared to the rest of it, which is produced more like a substitution reaction after.
Yes, yeah. Thank you for this. The answer is very, and hope there's more future studies. I hope that there are more future results from your groups as well. Yeah, in this.
Thank you.
Yeah. So, is there any other questions before we go to the next speaker? From
Dr. Eugene, maybe I want to ask one question to Fiona.
Yeah.
Yes, Prof.
My question is, how important is halocarbon from plants, isn't it, such as from seaweed, compared to halocarbon from anthropogenic activities, for example, from industrial activities that produce halocarbon to the atmosphere?
Well, you can separate them because one is anthropogenic, and most anthropogenic compounds, they are long-lived, and the impact on the environment is more, serious than these short-lived compounds. But short-lived, we can't just ignore it as well, although the role of it in the environment is not as great as, or even the amount released is not as huge as what is being released by man-made, the anthropogenic halocarbons. Yeah, and these normally the short-lived halocarbons that are being produced, they are very it's only less than 6 months. So it happens that in this region where we are in the tropics, it's more significant because it gets transported vertically than any other regions of the world. So, and this happens to be one of the region with large-scale seaweed farming. Yeah.
Thank you very much, Dr. Fiona.
Thank you, Prof.
Okay, yeah, thank you, Prof. Tariq. Okay, if we don't have any other questions, thank you, Dr. Fiona. Yeah, thank you for your talk. And and then we will move to the next talk from Dr. Po Tin Lim also from Institute of Oceans and Earth Science, University of Malaya. And the topic of the presentation is benthic harmful algae blooms and associated human poisoning due to aerosol toxins. Yeah, Dr. Lim, yeah. Please.
Okay.
Yeah.
Thank you, Dr. Tom. If you can see my slide.
Yes, yeah.
The right positions. Yeah, okay. I hope you see all the slides that I have. First of all, thanks to SOLAS and Prof. Talib for the invitations. I try to share a bit of the work that we have done over the last 2 decades related to harmful algal bloom, and to bring up some of the topic that might be really related to SOLAS, and also how harmful algal bloom and the aerosol that produce cause public health concerns. And we have several years of work related to these particular topics based on our work in Perhentian. So I think for those familiar with harmful algal bloom, that you probably aware of, it's a global issues, and it has socio-economic impact due to the increase of occurrence of algal bloom that causing, you know, not only losses to marine cultures, but also cause contaminations in seafood and cause mortalities of finfish in marine cultures and so on. And aerosol poisoning is one of the issues that less given attention in these regions. So I think it is also important for me to raise, there are international programs that existing to really look at the harmful algal bloom issues. And one of the programs that I would like to highlight here is Global HAP, that have been started with the JOHAP program. And from 2016, this program actually was supported by IOC and SCORE to continue to look at the global, to better our understanding and predictions of HAP, and also to manage and mitigate the impact of HAP. So if you would like to know more about Global HAP and some of the regional program and international program related to HAP, you can go to the Global HAP info webpage to look at that. So of course, you can also contact some of the members involved in this Global HAP program, including the chair, Elisa, or me, myself, to see is there any others potential collaboration related to aerosol and harmful algal bloom. So I guess if you look at this particular illustration, you will see that the HAP issue is quite complicated. We have things that related to you know, shellfish poisoning that have been traditionally managed and mitigate, like paralactic shellfish poisoning that happened since the 1970s in our along the west coast of Sabah, in Philippines, and Indonesia in recent years. So those are a typical type of shellfish poisoning that we have good understanding. And with the recent increase of marine cultures in the recent years, we also see that the impact due to algal bloom to our marine cultures also getting very, very severe. And of course, those are the conventional algal bloom that causing impact in our region. So, and another type of harmful algal bloom event that happens not at the surface, but at the bottoms, at the benthic ecosystem, the ciguatera fish poisoning that happens, and at the coral reef, where the toxins come from some of the microalgae, some species of microalgae that transfer through the trophic levels and getting to higher trophic levels and cause some of the fin fishes and some of the coral reef fishes become unsafe for consumption. So I think that is something related to benthic or benthic harmful algal bloom. That is the name that we have given for this sort of harmful event to public health. So we are seeing more and more cases. And of course, if you try to look at Ciguatera fish poisoning, you will notice that this group of benthic dinoflagellate are commonly associated with coral, with seaweed, and in our coral reef ecosystem. And if you look at here, these are the type of how toxins actually transfer to higher trophic levels, to barracuda, to snapples. And these are common vectors of fish of Ciguatera toxins. And when it comes to this sort of Ciguatera fish poisoning, we know that we have the vectors that cause human health issues. But what about the aerosol? I think that is a different route of transport happens in our coastal ecosystem that we don't need a vectors to cause poisoning. When it comes to Ciguatera fish poisoning, there are two types of toxin, the mycotoxin and the ciguatoxin. So they cause clinical symptoms like gastrointestinal, neurological, and in very severe case, it can cause cardiovascular symptoms. So over the last few years, we are seeing more and more cases, but mainly confined to the coast of Sabah. You can also refer to one of the case report from Malaysian medical journals that one of the cases that we reported in 2018. So aerosol poisoning happens also similarly to Ciguatera. What happened is the bloom happens at the bottoms of the coral reef or to the substrate, that it actually produce when it get into the surface. When the bloom reach very, very high density, it come to the surface similar to the one in the figures that show here. Okay, so in the figure D, that the photo D, that you can see that that sort of algal bloom event release the toxins, come to the air and ocean interface and release to the coast and cause human get irritations, and especially when it comes to the respiratory system. And of course, those are several other types of kind of illness that responsible due to the bloom of this benthic dinos. Of course, there is very specific dinoflagellate species that able to cause this sort of problem. And if you look at here, these are the countries that have been affected by the dinoflagellate obstructions over the last more than 2 decades. And since the early 1990s, respiratory symptoms have been repeatedly observed in humans. So, and when researchers from this region find out that it's actually due to the bloom of obstructions, a very common benthic dinoflagellate species in the Mediterranean. So, and the study also showed that these particular species are able to produce the analog of palytoxins. So palytoxin is one of the most potent marine biotoxin known so far. So I guess that is not really a good news to know when we have our coastal area are full with the dinoflagellate that are able to produce toxins, not only produce, but it actually get into the surface and get into the aerosol and cause people that stay very close to the sea to suffer from illness. I guess that is the reason why study on benthic hub have been increasing supported in the region because of the health human health concern. In addition to that, because of the algal bloom due to this particular benthic species, some of the shellfish mollusks are also contaminated with palytoxin and the related toxins produced by obstructive species. So if you look at here, I guess it will be interesting to see that since the 1970s, when the species was first reported from France, and you will see that there are a number of only from 1998, 20 over years later, you see that people suffer from some sort of illness due to this sort of algal bloom event. So, but there are very limited information from our side. So, but if you compare to the European side, this is the region that have been various monitoring program and research have been conducted since the late 1990s to look at these particular issues. And if you look at the map, this is the paper that published early this year, and we are not sure. These particular species are actually quite common. If you look at the green color and the yellow color, you see that there are two different genotypes that belong to the clade A and clade B. That we can clearly identify based on genetic information. And in Perhentian, we actually have both the clade A and clade B. So this doesn't seem to be a good news to know that we also share something that similar to what they have been reported to cause problem in Mediterranean Sea. So, and what about when it comes to this, the clade A and clade B, the differences is those clade A, those from clade A actually produce more potent ovatoxins or from Ostropsis ovata, and it has high toxin potentials compared to those come from clade B. So it means that a similar scale of bloom, the one from clade A are causing more severe problem because of the high toxin potentials. So these are the chemical structures. Because I'm not a chemist, but I can clearly tell you that chemical structures, they can be clearly divided to the palatoxins. Very similar to the ovatoxin is very similar to palatoxins in terms of structures. Very long change polyethers, and this was also some of the derivatives that have been reported based on the analysis by LCMS from Ostropsis species. So it means that there are many species that are producing various type of analog of palatoxin and ovatoxin. That these are the toxins that causing various kind of issues related to aerosol poisoning in human beings. So what about in our waters? So actually we started work related to benthic harmful algae and especially Ostropsis this for quite some time. So we know that we have good species diversity of Ostropsis from Perhentian all the way to Sabah. And those species in the early days, that was quite some time already, since 2001, they produce hemolytic activity, and genetically they are actually distinct. I mean, for some of the strain that we know from the European waters. So, and we also started some work a few years ago and completed the work and to look at the Perhentian Island and one of the island nearby called Rawa Island, to see how this benthic dinoflagellate species actually change. You know, there are not only Ostropsis, but also those responsible for gambit, for Ciguatera fish poisoning, and some other toxin producers that I would not have the time to cover in these presentations. So I will look at specifically to Ostropsis, and we are using non-destructive method, means that we don't have to collect coral to look at the species abundance, but we are using one non-destructive method developed by Tester in 2012, and then we improvise it in 2013, and then we have some result also from our study from 2018. It's a very simple fiberglass mesh that we use, like mosquito net that we deploy and we collect after 24 hours in order for us to quantify the presence and abundance of benthic hub community in the waters. So this is some of the data that you can see here. This is gambit Ostropsis, and also in relations to other species that we have samples. And if you look at here, the species actually present differently at different type of substrate, and we can clearly see that our method are able to collect and quantify the presence and also quantify the presence of this obstructive species in the sample that in area that we have deployed. So, and interestingly, from the work that from Young 2018, we actually see that obstructives didn't have the similar substrate preference. So these are the coral, turf algae, sand, and coral rubbles and macroalgae. Those are the different habitat, microhabitat that we have a look at, and compared to coral covers. So they actually have some sort of preference toward the coral covers, and those with and we actually confirm the presence of highest numbers in area with coral compared to other BHAP species that have slightly different preference. So this is some of the data. Every dot represent one particular samples, and you can see that in terms of obstructives, they have hard coral coverage, and in terms of this is the distribution over over the depth from 0 to 5 meters. You can see that they are clearly distributed more towards the photic zone. The higher photic zone means that the shallower waters, and but not to at the deeper water, like more than 15 or more than 10 to 15 meters, that you will hardly see the presence of this particular group. So when we look at this sort of data, of course, seasonally, the distribution, the abundance actually change because of the monsoonal drivers. And when we look at this particular obstructive species and the bloom and the presence in Perhentian, is there any risk due to aerosol poisoning in our region specifically, and based on the data that we have? And what are the triggering factors of the bloom? So, and I guess, and when we look at the toxic clade of clade A versus clade B, we have toxicity data that to show that we have higher numbers of clade B compared to clade A. It means that over the species compositions, means that the risk is lower compared to the area like in Mediterranean that they have mainly all clade A. So I guess we are still at the early stage to understand what are the triggering factors. But I guess one particular factors will be the temperature elevations. So we are trying to look at that in the subsequent study, how climate change and temperature elevations will increase the risk of this type of aerosol poisoning in our waters. So these are some of the, you see that BHAP generally occur at various bottom substrate, but they have certain type of preference and optimum at different levels. And study by others also show that the global SST increased by 1.4 according to tester might promote many hub event like what already happens in some of the regions right now. So, and so the issue of obstructive bloom poisoning are no longer confined to Mediterranean, and we have latest report from Brazil, from New Zealand, from Australia that indicate that there are experiences various type of poisoning or bloom related to obstructives that we have to pay attention to. So I think I come to the end of my presentations, and this study actually highlight that there are various substrate differences that actually influence the distributions of BHAP in a very complex way that interact with parameter factors. And BHAP dataset, the one we have obtained, will be important for our future monitoring if we want to assess the risk due to this sort of aerosol poisoning. And overall, the risk is low at the moment because the abundance that we have recorded in Perhentian is 2 magnitude lower to those reported in Mediterranean Sea. But of course, any triggering factors that increase the abundance of obstructives in the waters, that will certainly elevate the risk to this type of aerosol poisoning in our waters. I guess with that, I will end my presentation here. Thank you very much.
Okay, yeah, thank you, Dr. Lim, for this interesting presentations. Yeah, so we have plenty of time for questions and also comments, questions from members on the floor. Any questions?
Dr. Lim, maybe I have questions related to aerosol that you mentioned in your presentation. Is it this aerosol within the water ecosystem, or this aerosol can go up to the atmosphere and affect other species or human beings?
Yes, I think that is the intentions that I would like to highlight. Probably I missed that in the early part of our presentations. A lot of bee harp and obstructive bloom in Mediterranean causing human illness is actually bloom in the waters, and the air that they release to the atmosphere bring to the shore and cause people that stay very close to the shore suffer from the illness that I mentioned earlier. So, and for monitoring in the Mediterranean Sea, once they monitor the presence and the high numbers of this particular species, they stop people from going to the beach. So I guess that this is a different way of poisoning that people look at. So now people are not allowed to go to the beach because of algal bloom happens in the waters. So there are thousands of cases poisonings happens over the last 2 decades.
Is it this kind of phenomena also happen in our region?
No,
no,
not a single one. Yes, not a single one so far reported in this Western Pacific region. So, but the presence of the species, yes, we have recorded the presence of this particular species throughout the Western Pacific region. So, like what I mentioned earlier in my presentation is our numbers, the cell density that we have recorded from Perhentian is at least 2 magnitude lower compared to what they have reported in Mediterranean. So it means that that is the good sign. So our are not deteriorating high until we have the cell numbers that high to release enough toxin to cause poisoning. But it doesn't mean that it will not happen. It could be somewhere, and also because our study is only limited to Perhentian, it might have it in some other coast in our waters, but there's no other study, and it's not fatal enough. So people might suffer some, irritations to your eye and, respiratory illness, but people might not associate it with sea spray. Right? I guess that is also possible explanation why, the very few, almost no cases reported from this region.
Yeah.
Do you know somebody who I want to ask about any effect that monitor this aerosol from ambient air? Means that, for example, our team always collect sample near to the shore, the beach, to see the influence of marine aerosol toward aerosol in ambient air. Do you think, or do you find any kind of studies that monitor this aerosol in ambient air within the coastal ecosystem?
Yeah, from Mediterranean.
From Mediterranean.
Yes. Okay. From Mediterranean, yes, they are monitored, and they can actually correlate the data from the bloom in the waters, the one come to the surface, and the one get into the air. So they have completed those sort of study based on the the regular bloom that happens in Mediterranean Sea. Yeah. So, but not in our region.
Okay. Thank you very much, Dr. Lim.
Thank you, Prof. Talib. Actually, Dr. Lim, I have a follow-up questions related to Prof. Talib's questions. Yeah, actually, the aerosol toxin that you are talking about, if it exists in the atmosphere, is there any studies on how long can this aerosol toxin travel from the beach? Can it go far into the land, or just it will be? Yeah, is there any studies related to this? Because aerosols can travel far from in the atmosphere actually. Yeah.
I
What do you think? Yeah.
I think based on the study in Mediterranean, I think the latest one they have they found, of course, the correlation between the one in the waters. When we have high numbers of substances, then you have high concentrations of ovatoxin in the air. So, but I guess the monitoring program actually stopped people from going to the beach, but there's no specific region. I don't think they travel that far, because if you look at the coastal community in Mediterranean, they stay very, very close. So what I know is people have apartment that facing the sea near the shore. Those are the people that will suffer from this sort of algal bloom and the aerosol poisoning, but not those stay far from. I don't have the exact numbers, like how many meters that you are safe. So, but I guess that is something to look at. And the same thing applied to us when we first started to look at the benthic harmful algal bloom. We are looking at those from the source, but without we need good chemists to look at the one in the waters, and the air chemists to look at those in a MS, right? How far they can travel. So toxin is well characterized. So I guess that helps a lot. We know ovatoxin, A, B, C, D, and so on. As long as you have a LCMS, then you can do this characterization quite easily, because reference material is already available, and we have the cultures that those produce that sort of toxins in our lab. So that might ease the way how we want to do, some simulation study, and in the lab, how much toxin released if you culture them in large quantity. That might be something worthwhile to consider if you want to estimate the risk for other species that found in our waters and to our environment. But because I think from our side, we need the chemists to work on that aspect. I'm a biologist, so, and I guess we are hoping also to have collaborations, the chemists that interested to look at these aerosol toxins that come. And from New Zealand, there's one very interesting cases. People clean up the aquarium tank, the seawater tank that they keep it for seawater aquarium. And the people actually, during the cleaning process, they suffer intoxication. So that means that it's possible to have simulate that sort of experiment, because we can easily culture them in the lab. So it might be also another form of risk if you are keeping marine aquarium at home in a confined area.
Yeah, agree. And it's interesting. Yeah, we can from this SOLAS we can have more collaborations on this as well in future, maybe. Yeah. So any other questions for Dr. Lim? Is there any?
Yeah.
So yeah,
Right.
Yeah, go ahead.
Thank you, Dr. Lim, for the nice talk. So so I'm wondering, as you probably have been aware of it already, so there is a SOLAS Indoors project which investigates the aerosol productions of the Great Barrier Reef, and it seems that the Great Barrier Reef is a significant aerosol production source. So I'm wondering if the amount of the aerosol production is like comparable to the aerosol production of the coral triangle in Southeast Asia. And then maybe that, I mean, the coral systems are more close to people in Southeast Asia than it is the Great Barrier Reef to the Australian coastal lines. Then probably it will impose like more severe health or environmental issues if there are HAB release these toxins, and then the aerosols carries those toxins. So I'm just guessing.
I think when we first started the benthic harmful algal bloom research, our main focus is related to ciguatera fish poisoning because our dependence on reef fishes as part of the seafood protein. So, and that's why the emphasis on another species or another genus that called Gambidiscus, because they produce ciguatoxins that transfer through the food chain. And with the degradations of coral reef, this particular group increase in numbers. And if you increase in certain numbers, the toxin accumulate in the higher trophic level increase, and when come to the top predators, they are no longer safe for consumption. I think that is the main reason why we have a lot of ciguatera fish poisoning happens in Caribbean and also in the Southern Pacific island country. So I think that is the focus for many decades, because a lot of people got illness and they have no other source of protein unless they get fishes from coral reef. So only until very recently we have better understanding that this is a source and this is a toxin, but it's difficult to monitor because individual differences when come to the vector fishes. So I think yes, when degradation of coral reef cause the change in the benthic, the microorganism, the microalgae community, and some of them are the one I mentioned in one of the slides are those responsible to cause problem. And obstructives is one of them. Gambidiscus is another one that certainly will cause some problem, whether it's the seafood is no longer safe or the aerosol. But of course, we know we have the numbers of species commonly in our coral reef. But the thing is, and how much contribution, how much productions of aerosol that get into the air, and not all the area have been surveyed in our coral reef triangle, the CTI. So I guess those are the topic to look at. If someone is interested to look at the BHAP and the aerosol productions. So it will be something important to consider for the futures. Yeah, it's just like eutrophication. We have hypoxia, and hypoxia cause fish kill, and those are all interrelated in our coastal communities, in our coastal ecosystem. Yeah, I hope I answer your question.
Good, thank you. I mean, we could still discuss later.
Yeah.
Okay, yes. So is there any more questions for Dr. Lim? Yes. So if no, then yeah, thank you, Dr. Lim, for presentations and nice conversation here. Yeah. So thank you very much. And yes, since Dr. Vanessa is not available for the talk, so what is Dr. Mohammad Sharul here? If you are here, maybe we can start with your presentations. If not, then so should we take a break, moderator, or secretariat, or wait for?
Maybe we have like 7 minutes break. See if Shahur will be here or not.
Yeah, I think I agree.
Yeah. Okay, then we will have a 7 minutes break or 10 minute break.
Yeah.
Yeah. Then we will be back before the 5 minute breaks actually. The next will be start at 4, right? So we can back at 15:58, 59 something. Yeah. All right. We can take a break. Okay, is Dr. Mohammad Sharo here already here? Right. Yeah. Maybe we can start our final talk of these sessions given by Dr. Mohammad Sharo Muhammad Nasir.
Hi.
From University of Kebangsaan, Malaysia.
Yeah.
And the presentation topic is on halocarbon and its potential sources over land and maritime regions of Malaysia. Yes, over to you, Dr. Sharo.
Thank you. Should I share the slide or you have already my slide?
I think you can share your slide. Yeah.
Okay. Okay. Assalamualaikum warahmatullahi wabarakatuh, and very good evening here in Malaysia. Today I would like to give my presentation entitled Halocarbon and its Potential Sources over Land and Maritime Region of Malaysia. This is a collaboration between Universiti Malaya, University of Cambridge and UKM. Okay, just a short introduction. This is our group back here at UKM. I think most of you are great scientists, and or everybody probably knows what is halocarbons. Halocarbon is a chemical compound that we can observe in atmosphere, contain one or more carbons atom and link with halogenated compounds such as bromine, chlorine, iodine, fluorine, and so on. And what is the most important characteristic of these halocarbons that the halocarbons can contribute with their reactivity towards ozone depletion. So this is catalytic destruction of ozone, where halocarbon participate in, where it break ozone molecules to single oxygen, combined with halogenated compounds, depending which is whether it's bromoform, chloroform, hydrochloromethane, and many more. So this why scientists discovered halocarbon potential to give a significant impact on ozone depletion. So that's why halocarbons are very, very important study throughout the world, including Southeast Asia. And what the other important information on halocarbons. Halocarbons mainly emitted from biogenic sources, mainly from ocean region. It can be emitted by microplankton, micro and macroplankton, such as seaweeds, microalgae, and many more. And halocarbon can be divided by two groups, which is long-lived, where normally the lifetime of this compound can reach 100 of years, and while very short-lived is normally can be less than a few months. So it depends on the characteristic of its dilution process and chemical reaction in atmosphere. So this short-lived and long-lived depending on these factors. During my PhD thesis, me and myself at UM during that time and University of Cambridge, we have proved that equatorial lines such as region like Malaysia can be a getaway of these halocarbons up to the stratospheric level. So this is why significant to study about halocarbons in the ocean region. Okay, another issue, or not issue, another information that lead or motivate us to do halocarbon measurement is due to lack of observation or monitoring in Malaysia, especially. If you can see from this map, there are a lot of stations and includes cruise observation, ground-based observation. There are a lot, but in Malaysia we are still lacking. This is map actually based in during 2009. So I think there are a lot of groups now, especially from the University of Malaya, that conducting a lot of observation on this halocarbon. Okay, this is a name model run by Pai et al. 2011, and it shows the getaway of this halocarbon mainly contributed from equatorial line. Okay, in this presentation, I would like to share with you from cruise observation till at maritime and land observation via cruise and ground measurement. Okay, our methodology, normally we use direct sampling, such as in situ sampling or ex situ sampling. So for ex situ sampling, we use flask canisters to trap gases or air into a 3-liter flask, and then we brought back to laboratory to determine the species using GCMS. And other than that, we use in situ gas chromatography or portable that developed by University of Cambridge, known as micro-direct. So micro-direct is a GCFID that can measure various types of halocarbon compounds. Okay, this is back in, I'm so sorry, it's a typo here. It's not 2019, it's a 2009, where we conducted a long cruise from Peninsular Malaysia to the Sulu Sulawesi Seas near to Tawau, Sabah. So you can see there were several points that I collected using 3-liter flask from coastal to open ocean. And back after 2009, so there are several years later, in 2017, in collaboration with UMT, University of Malaysia Terengganu, we did just a short 14 days cruise observation from the north coast of east coast of Malaysia to south coast east coast of Malaysia. You can see there are many points, but here compared to the previous cruise, here we collected only air, and this one, this observation we collected water sample, a seawater sample. Okay, for air, we discovered at Strait of Malacca, we observed high bromocarbons such as dibromomethane, CH2Br2, and bromoform CHBr3. And this is in the fact due to, we believe from our published paper, we prove high seawater that contain high chlorophyll A will have high halocarbons concentration above the sea water. So this is the percentage. Mainly, we discovered bromoform, one of the highest compound among other halocarbons during the cruise in 2019, followed by CH2Br2, CHBr2 Cl, and CH2BrCl. So these are the 5 major compounds that we detected from the GCMS analysis. As I said just now, if you see at the Strait of Malacca near to the Port Klang, high chlorophyll A content in the seawater, that actually the reason, the region that we discovered high halocarbons concentration. At all high chlorophyll A content in the seawater, we discovered high halocarbon, not just at the Peninsular Coast or Strait of Malacca coast, but we also found high concentration at near to the coast of Sabah, especially near to Kunak and Tawau. Okay, at the same year, we deploy a portable GC, as I previously mentioned, micro-direct, developed by University of Cambridge, where we deploy at coastal of Tawau, the one where we found during our cruise observation high concentration of bromoform. So when we deployed the GC and we discovered the same things, high bromoform and high dibromomethane. So it's proven by both methods, by in situ and ex situ experiment. So this is the fact due to the biological activity. Okay, this I just want to share with you the land observation. Okay, we conducted a 2 years observation of halocarbons at Danung Valley. I think there was a presentation this morning show nice facility in Danung Valley. So at the same location, we deploy the same gas chromatography, micro direct, and we shown that we deploy the inlet about 80 meter at the top of the tower. So here we show high concentration of bromoform and dibromomethane. Here we also do comparison with other observation by University of York and University of East Anglia, where our result is a bit higher than observed by other university. I think this is due to different technique because UA and University of York use GCMS, while we use GCFID. So it depends on the sensitivity of the detector. And then we try to compare between coast site and also forestry site. And if you see when we overlay both results, at the coastal site show increase of the bromoform concentration. So again, mainly source like biological source or biological productivity nearby the coastal site were mainly the source of this emission. Okay, back in 2017 just now, with collaboration with UMT, we collected seawater. Since we don't have any data yet inside the seawater, so we did this cruise, a short cruise, 14 days, and we discovered bromoform and dibromo, the same species that we discovered in air, observed in seawater is quite high concentration. During this time, we did two analysis or two sampling, which is one is at the top and second is at the bottom. So you can see they are very the concentration is very following the different depth. And if you see at the top of the seawater, about 1 centimeter of the seawater, we discovered high concentration of bromoform, dibromo, and dichlorobromomethane. Same thing here at each station. You can see, I think due to high productivity, more compared to at the top compared to the bottom of the seawater. Okay, to see the potential source, whether the bromoform and dibromoform and other brominated compounds, we do correlation between each species. So when we plot both dibromo and bromoform, we can see a good linear correlation, and it shows the potential of bromoform and dibromomethane is coming or emitted from the same source. And similar to in the seawater, both brominated compounds show high correlation. Okay, by Yukuchi et al., we use the same approach by Yukuchi, where this graph basically is to use to calculate the emission ratio. If you see the linear line is the dilution line, and the dashed line is the chemical decay line. So if you see all the data is approaching the chemical decay line, is due to the lifetime. Like bromoform and dibromomethane has shorter long lived, and this is why the plot showing close to the chemical decay line. Okay, at the bottom, at the top of the plot, you can see there is a point, different colors. So the black one is Yukuchi, we call it point C, and our cruise point D. By using the same
approach by Yukuchi, we estimate the emission rate of the bromoform about 32 gigagram per year, and also the dibromethane 6.4 gigagram per year. As a summary, both our cruise and our air and our seawater correlation show most of the bromocarbons are correlated well, and it shows that we are close to the sources. Either can be seaweed or phytoplankton. So both these sources emit the same species bromoform and dibromo and other bromocarbons species. From our chlorophyll A satellite data, we did an analysis, and we also found that a strong correlation between productivity or biological productivity and halocarbon concentration. So it shows again, mainly the source are nothing else is the biological sources. Okay. I think that is all from my presentation this evening. This is just my acknowledgement. I would like to thank mostly Ministry of Science and Technology Malaysia, Malaysian Royal Navy, and also UKM Internet Grant for both experiment air and seawater of halocarbon analysis. These are our publication from previous cruise. And thank you.
Okay, thank you, Dr. Sharo, for these nice presentations. All right, we have time for a few more questions. Any questions from the members of the floor? Maybe while waiting for the questions, Dr. Sharo, I think I would like to ask questions. I think, yeah, you did a very good job from this measurement of halocarbons in Malaysia. And from your results, I think it started in 2009, right? The first measurements in Malaysia. Is this measurement still ongoing until now? So you already have almost 10 years plus of data. Is there any difference between the trend of this halocarbon in Malaysia? Yeah.
We are still conducting similar approach, similar experiment, but we are focusing on ground-based measurement. We deploy a gas chromatography, the same GC that we used at the previous publication, where we deploy at a tower belong to IOAS Universiti of Malaya. I think maybe Dr. Fiona is here. We stopped the data since 2017. So I have data about like 5 or 4 years from 2010 to 2016. I think I still have the data because my previous PhD student Bakis did some analysis. And then, as far as I know, University of East Anglia (UEA) still collecting flash sample at the same location at Bacho at the east coast of Malaysia in Kelantan.
Yeah.
So we are hoping to combine all this data. We hope that we can, try to show next conference or something. Because I'm really sorry. I'm supposed to analyze all this data, but due to the time consuming, I managed only to show 2009 data.
Oh, it's okay, but I think it will be interesting to look at this long-term trend. Yeah.
Yeah, I think my feelings that the constellation will be so different compared to the 2009 data, I believe.
Yeah. Yeah, it will be interesting to look at this. Yeah. So yeah, thank you. And is there any other questions from? If any more questions? If no, then thank you, Dr. Sharo. Yeah, there's someone asked in the chat box, Dr. Sharo. Thanks, Dr. Sharo. Can I have more information on the satellite that you use to compare the data? Which satellite? Yeah, maybe Dr. Sharo, you can.
Yeah, we use, if I'm not mistaken, Modis satellite and seaweed.
Yeah. Okay, so
Yeah,
any more?
Just drop email to me. I think I still have the chlorophyll A data. Probably I can share. No problem.
From Hannah, you can drop an email to Dr. Charo. Yep. Yes, so if no more questions, then thank you, Dr. Charo, for your presentations. And let's give a big applause to all the presenters in these sessions. Thank you very much for your interesting presentations.
Thank you, everybody.
Yeah.
Bye.
Yeah.
Thank you.
Bye. So I will pass back to this session to the secretary. Yeah. Thanks.
Thank you very much, Dr. Yijun Tam, for being a moderator for this session. So now I want to pass this program to Dr. Lily from SOLAS IPO to conduct the discussion session that involves several researchers, panelists from the participant. Over to you, Dr. Lily.
All right, I will take it over from here. So thank you, everyone. Thank you, all the speakers today for your excellent talks. And thank you, thank you, Talib. Thank you, Yijun and Tachanat for chairing the sessions. And especially a big thank you to all the audience for staying together with us until the very last session of today's workshop is the panel discussion. And for today's workshop, we really cover diverse topics, which means there are rooms for interdisciplinary or multidisciplinary collaborations. So several speakers mentioned already, this region is very important. It's the driver of the climate at multiple scales. And it is in terms of its ecosystem service and the societal economical impacts, and it is super important to study this region. And with this panel discussion, we would like to know what are the priorities of SOLAS relevant research in this region, and what are the regional needs, and how we could work together to answer those scientific questions. And please, all the panelists and all the speakers, and if any audience would like to join the discussion, please turn on your cameras so we could start a discussion already. So maybe Talib, you want to go first?
Okay, thank you very much, Lily. First of all, I would like to thank to all the keynote speakers, as well as invited speaker and oral presenters for a very good presentation today. So I learned a lot from the presentations. So based on what mentioned by researchers, all the presenters today, we found that there are so many related studies based on SOLAS related activities has been conducted in Southeast Asia. So for this, I think for the moving forward from this workshop, it is very important for us to work together on SOLAS related research. As we know that in Southeast Asia, we have several institutes, I think from different countries in Southeast Asia, from Thailand, you know that from Indonesia, Singapore, the Philippines, and Vietnam, and also other countries. But the main challenge for us here in Southeast Asia is for us to work together on this related topic, because I found that there are so many researchers involved with this study, but maybe many of us still work alone or not know between each other and not work together on this related topic. So for me, based on the presentation today, it is good for us to start to work together on this ocean related research. based on the activities based on SOLAS related activities. So from our initiative for us to work together, maybe we can have many other potential research project, publication. Also, we can bring young researchers to work together on this interesting topic. That's my early point, Lily, for us to start our discussion.
Yeah, that's a good point, and I fully agree. And yes, it seems yeah, we need more communications to know what each others are doing and what's the overlaps and what's the space for collaborations. And so Talib, since you are very experienced in those collaborative grant applications, I mean, there are some regional collaborative frameworks for people for this kind of international regional collaborations, such as the Asia-Pacific network, and you are very experienced in that. So could you please share some experiences?
Okay, I'm involved with several research groups, I think, in Southeast Asia. I think here we know very well Prof. Bala from NUS. When I came back from UK at the time, I met Prof. Bala and Prof. Kim An, I think two prominent researchers in Southeast Asia that work on air pollution and also air quality related studies. I think for us to explore this kind of research grant, for example, APN, Asia-Pacific Network, we need to have collaborations. I mean, we need to have relationship between each other. And usually the panel look at our experience on how we work together, our previous publication together, on how we work together. This, I think, are the main point for us to explore this kind of research grant. So luckily, at that time, I worked together with main researchers in Southeast Asia, such as Prof. Bala and Prof. Kim An. We also work within IGEC, International Global for Atmospheric Chemistry in the Monsoon Asia region. So Prof. Kim An usually invited us to Bangkok at the time as a young researcher to work together, and then from that collaboration, we can explore this related research grant, for example, Asia-Pacific Network for Global Research Change. That's from my experience, Lily.
Thank you very much. And Professor Bala, so yeah, since you were mentioned, and since you are get a lot of involvement in the ocean acidification community, and could you please maybe share some experiences with the audience, if, like how the community could be benefited from getting involved in those networks?
Yeah, well, I fully agree with what Talib already articulated in terms of the need for us to come together as an interdisciplinary research community, exchanging knowledge with each other, identifying knowledge gaps that need to be filled, and then apply for an external grant, something like APN, or something beyond that, maybe United Nations grant or something. But sometimes, based on my experience, if we start looking for the right funding opportunity for us to work together, it may not happen so soon. But instead, we can start working together on an informal basis. So that will set the stage for us to sort of, find the right project, a cross-cutting theme that we can work together. So ocean acidification is an example. There are several other projects we could possibly consider. For example, biomass burning that Talib and I have been working together for quite some time. That's a complex issue. And as I indicated in my one presentation, the atmospheric deposition of pollutants, air pollutants derived from biomass burning have a huge impact, not only on human health, but also on marine life, and especially because of coastal eutrophication. And the paper that was published by an Australian research group soon after the 1997-1998 fires we had in Sumatra and Kalimantan. And they made an interesting observation east of Sumatra. So they found a massive coral reef death. It happened all of a sudden. So they started wondering as to what could have caused the problem. And the hypothesis made then, it is the deposition of micronutrients like potassium, which we never anticipated. And incidentally, potassium is used, as Dalim knows very well, as an indicator of biomass burning. And it's commonly found in soil, especially in peat soil. It's also found in biomass and stem. So when you have all this uncontrolled other wildfires, potassium is kind of emitted. And so that sort of deposited into the ocean, being a micronutrient, it could trigger algal bloom. So I'm just giving an example. So I think it's good for us to come together and start working on an informal basis, and then apply for an opportunity to submit a grant proposal.
Yeah, thank you, Professor Bala. That's a very good point. I mean, there are a lot of topics that they are multidisciplinary, which just need the collaborations of people from different research backgrounds. And what you just mentioned is definitely what SOLAS is interested in. So actually, we are establishing a working group, or even we are targeting a UN Ocean Decade program on this topic, the fire, the volcano emissions, and the burning, and then how this event will affect the climate and the ecosystem. I mean, yes, as you said, on one hand, it's harmful to a lot of creatures, to the ecosystem, but on the other hand, it also brings micronutrients to the ocean environment. So yeah, we definitely, and by the way, there will be relevant discussion sessions at the upcoming SOLAS Open Science Conference. So everyone, if you're interested, please join us.
Sure. The other part I would like to mention would be something to do with marine aerosols. And we have been working on aerosols which are of anthropogenic origin, mainly. But in this part of the world, in Southeast Asia, little is known about the characteristics of marine aerosols. And some of them, could be also acidic because we have the sea salt. And the sea salt emission, could lead to corrosion-related problems and so on and so forth. So it'll be a good idea. It doesn't cost us much money. It'll be a good idea for us to capture marine aerosols and do some chemical analysis to find out the specific signature of marine aerosols as compared to anthropogenic aerosols. And that would be very helpful in terms of source apportionment. So usually when you do the source apportionment of aerosols in a particular country, we make some assumptions about the contribution of sea salt. And that assumption can be fundamentally questioned. And so in that regard, it'll be good to collect marine aerosols and then exchange with others. For example, I might be collecting marine aerosols in Singapore. I can ship them to other research groups who may have expertise in other areas in terms of chemical analysis. And then we could go for a joint publication or vice versa. So the most important thing is to start talking to each other and then work together as much as possible, and then look for funding opportunity. For that, there are many projects we could think of, and each of us is working on a different theme. So we can start sharing our ideas, thoughts, and then talk to Lily, who could sort of facilitate our collaboration. So that's probably one way to go.
Yeah, IPO would be always happy to offer any assistance. Yeah, thank you, Professor Bala. When it comes to the aerosols, maybe June, you have some ideas to share with us?
Yes. Yeah. Thank you, Lily. I very agree with Prof. Talib and Prof. Bala's the ideas and these comments about actually I'm still quite new to academic because I just started my academic job like a year ago. So yeah, and I'm very fascinated to see so many great research in Southeast Asia, especially in Malaysia and Singapore and Indonesia and so on this. And as an atmospheric chemist, I think, and a young scientist in this field, I think it's good that we can start talking in a smaller group instead, like in one session, like in team. Maybe, for example, in this SOLAS that divided into teams, maybe we also can do something like that, divided into some specific teams. For example, marine aerosols, those who work, or hydrocarbons, those who work here, so we can have a more efficient in talking and communicating with each others. So that and maybe some senior scientists can join into this group to give some comments or give some ideas and so on. So I think it's good to start with a smaller groups of scientists to start communicating first, and what we should do and what scientific question we are going to answer and how we can do it. For example, what I'm interested now is in halocarbons or marine aerosols or biomass burning, which is a unique place for Southeast Asia to study because other places do not have this kind of biomass burning effects on the marine. That they can't see it, but we can only see this mostly from Southeast Asia when there's a biomass burning seasons. So it is a very good place to start the research. And from my side, I hope that I can also will have in future we have more chances to come back to Malaysia or Southeast Asia to have some collaboration. Although I'm now based in China, but I think we should work together. Yeah, there's some of my thoughts now for now. Thanks, Lily.
Yeah, thank you, Jin. I think, I mean, in addition to those international and regional collaborative frameworks, as Zhiyu mentioned early this morning, there are some collaborative frameworks such as the China-Indonesia collaborative projects. So I think there must be similar collaborative frameworks in other countries, at the funding agencies of other countries. So we just have to talk to each other and then communicate with each other, sharing this information with each other. And when there is a nice topic we want to work together, then we could go for a proposal for it. And I fully agree with what Jin said. So yeah, we definitely, and as well as Bala said, we definitely has to get early career scientists involved. So one of the aims of this workshop is actually establish a regional panel. And I think the early career scientists should play a big role in this panel. And maybe as early career scientist representatives, Royston, and then Prof. Tachanat, you have some words to say.
Yeah. Okay, can you hear me?
Yes, very well.
All right. So yeah, thanks for. I mean, yeah, I've been in and out throughout the session, but what I can say as an earlier career scientist, I used to work with Talib in Malaysia, but now I recently joined Tanimoto's lab in Nice. So as an early career scientist in Southeast Asia, I think, of course, Southeast Asia is, for me personally, I think it's a unique environment with the phenomenon that happened. For example, a big scale of biomass burning and so on, and what Prof. Bala mentioned about the marine aerosol itself. So there are a lot of interactions that happen, whether it's a large scale or small scale. So it's worth to look into that kind of things. Of course, not for, I mean, what can be done, I mean, for the mitigation itself and so on. So as an early career scientist, I can see a lot of opportunities throughout the, big scale organization. One of the example is SOLAS. I've been get in touch with SOLAS for some time. Another one is IGEC. So in terms of collaboration, there are a lot of opportunities. So I personally encourage for other early career scientists in Malaysia, or soon to be one, to get involved with this big organization, and where you'll get connected in any dimension that you can imagine. So from there you can work with science and so on, for networking and whatsoever. So yeah, get involved with big organizations, and things will get started as an early career scientist. Yeah, thank you.
Yeah, great. Thank you, Royston, for sharing your stories with SOLAS. SOLAS as an international program, we do provide plenty of opportunities to early careers. In addition to the regional panel in Southeast Asia that we would like to establish, so we have the SOLAS Summer School, and we have Early Career Scientist Day, which is a dedicated event for early career scientists at each of the SOLAS Open Science Conference. So there are plenty of opportunities for early career scientists to communicate and networking with each other. And some of them, our summer school alumni, early summer school alumni have become the experts in their fields already, and they have established lifelong friendship and a collaborative relationship with with his peer researchers. So it is really important. Then maybe Tachanat, maybe you have you're also early career scientist, right?
Yeah. I'm thinking about we should start with regional synthesis, where we are currently are, where regional sensitivity take place, and what are missing gap in scientific milestone. Many issues can be combined together, like acidification and deoxygenation. That's for example. And we know that carbon pathway and carbonate system are complex. We should have sharing some observation measurements, or what we have to do regional synthesis. And we might combine or use other panel like IOC, GOOSE, Global Ocean Observing System, IO GOOSE, right? Indian Ocean, and Sea GOOSE, Southeast Asia GOOSE Observing System as well. And I agree that many other issues like aerosol and PM, it's still many other ways to go, like salt apportionment is still unknown, and long range transport as well. And yes, I just wish to mention about sharing some measurement and observation. That's might be a good start.
Yeah, actually this brings some idea to. So is there any possibilities to organize joint cruise? For China, here in China, there are kind of funding support joint cruise, but I don't know if there is any possibilities in Southeast Asian countries, there could be a joint cruise, and then people could to do the observations and the monitorings and the measurements together, and maybe even share the best practice, as Trang brought up in the chat box. She was asking the PCO2 measurement. So if there's any possibilities in Southeast Asian countries if there is any funding, if funding agencies are supporting this kind of collaborations. Any ideas in Malaysia or in Singapore, Thailand? We cannot hear you, Taran.
I have participated as a member of local organized committee for than 1 month. So today is very happy to join with the workshops, SOLAS workshop, and from the workshop, I got a lot of issues that we can put together in the marine science. In Vietnam, at the moment, we also have some study related to the ocean. And we also have some measurement for the pH.
Sorry, Karan, for the interrupt. It was not clear, but could you please say something? Not for clear.
Before that, maybe I can say something, Lily.
All right.
In our previous experience, actually, we work together with researchers from different regions. For example, by grant from UKRI, from United Kingdom or Europe. And then we work together on emission-related study, including from tropical forest as well as from tropical marine ecosystem. I think several of our invited speakers, such as Professor Cik Rahim, also involved with researcher from China. They also had, I think, cruise experience to monitor the atmospheric aerosol from oceans. So what I want to mention here, sometimes based on our experience, we alone from our country cannot do a big project because of maybe lack of fund and so on. So we need to work with others. But to work with others sometimes is quite difficult. So we ourselves maybe need to show our strength and maybe capabilities, so others want to work with us. I think there are many researchers here. For example, Fiona from IUS also worked together with a researcher from Cambridge who came here to work on this halocarbon. So that's what I want to mention. If we just depend on our local fund, sometimes the local fund is very small. So maybe we need to have something like for SOLAS, I think they are very familiar with SCORE. I involved with SCORE last time with Oliver Ball. Oliver Ball, I know based on, also I want to mention, is my mentor from Bala student. I know Oliver actually based on his work from NUS. So I met him, and after that we had one SCORE project. So because of this SCORE project, Oliver can come to Malaysia and China and then work together with us. So I think networking is very important for us, and maybe if we have opportunity for young researchers, for example, based on SOLAS information SCORE project, maybe we can involve these young scientists to work together with the prominent scientists from other regions. Thank you.
Yeah, thank you, Talib. That's a really good idea. I mean, SCORE is really a good platform. I mean, they encourage collaborations, and they like the topics that has not been touched yet. I mean, or very specific ones. So Fiona, if I understand your talk correctly, it seems like the short-lived halogen in the tropical environment should impose more severe environmental impact.
Yeah, if you compare,
so maybe,
yeah.
maybe that could be a SCORE working group.
Yeah, that would be great. Yeah, actually we could, there's just so much to be done. I mean, in this area, especially if we are looking at algae halocarbon, it's from the cellular level, from the enzymes up until the emissions and the fluxes, and then, you know, the modeling and all. So yeah, we don't have many people. I mean, we need a lot of people that could help with their own area of expertise in this to, I mean, provide a better budget and all. So collaboration is, I mean, is very important, needed.
Yeah, and yeah, I mean, there will be the SCORE call for working groups will be released on an annual basis. So we will always happy, the SOLAS IPO or the SOLAS SAC would always happy to, yeah, support SOLAS relevant applications.
Yeah, and it's good to have like mentors like Prof. Talin and Prof. Bala around, like to guide us, like the young researchers, the correct way to go. Yeah.
Right. So maybe Tran could have a try again, see if your audio connection is good enough. Not very well, at least from my side. How about others? Can you hear Tran well?
Yeah, it's not clear.
Unplug the headphone, I think you have. Don't use the headphone.
From my point of view, also in Vietnam, we can collaborate with all of you for the carbonate system dynamic. For this morning presentation, I'm very interested in that, and we also interested in for the modeling of CO2 from atmosphere to the seawater. So I hope that we can have a more cooperation and more publication. We can cooperate for the publication for the maybe not CO2, not for the carbonate system dynamic, but also for the other issue for halocarbon, harmful and blue, something like that. So for the networking and in this workshop today only our institute, but I hope that in the future we can attract more institute in Vietnam to participate in the network. And I hope that we can have a more action like the offline workshop or some project or some summer school for young scientists, so we can have a more collaboration. So that's all. Thank you.
Yeah, that's a good idea. I mean, we actually when SOLAS had we had an Indian Ocean workshop last year, so there was a discussion, and the Indian Ocean scientists, they would like to have some regional SOLAS summer school, and we think that was a great idea. I think that's similar for Southeast Asia. I mean, this could be something done. If we have the regional panel in Southeast Asia in the future, this could be, yeah, this could be on the task list of this regional panel. And so maybe if I'm wondering if there's any ideas from the audience, or Tachanat, please go ahead.
I think it might be a good idea if you continue some sort of like a routine webinar to gain and encourage more new faces. and shed light on them, we can have more people working on. Yep.
Yeah, so yes, we are, there is currently a SOLAS seminar series is running. So it's a quarterly event, but I mean, once again, if we have the regional panel established, we could definitely have the regional specific event. Like we could have a regional seminars that could be simply organized online, or when the travel is possible, we could, yeah, have the similar series hosted by different institutes in the region. That will be interesting, I think.
I actually really support that kind of activities, Lily, because I think, as mentioned by Dr. Tachanat, regional meeting, seminar, and so on, I think it's really encourage collaboration between us. So maybe we can think about that. And as you mentioned, that the committee within the region also we can try to think about that. And then from this platform, I think we can start to work together on this kind of very interesting topic.
Yeah. Oh, seems Tachanat is disconnected. I was just about to ask him a question. Sorry, never mind. All right, it seems actually there seems many speakers are still online, but I'm not sure if they are really here or not. Like, Faisal, are you there? Or probably not. Or if any other audience, if you would like to share some experiences, or if you want to let us know what's your need. So during the process of organizing this workshop, one of the interesting points that I noticed that is that among all the SOLAS 5 core themes, so the theme 2 is kind of missing. Theme 2 research is kind of missing in Southeast Asia. Actually, I was about to ask Tachanat.
Sorry, what is theme 2?
So it is the air-sea exchange of gases.
Okay.
Mm-hmm.
Yeah.
Since Tachanat, he is a theme 2 person, so I was about to ask him, but now he is get lost.
Actually, the one that involved with this theme 2 is Royston, because he the one that
we sorry to interrupt, but we did some work in Southeast Asia. I mean, but unfortunately, I couldn't. I mean, present some of my findings. But it is. I mean, Team 2 is seriously less explored in Southeast Asia. I believe there are large-scale cruises by a group from Germany, I think back in many years ago, to study the, for example, the oxygenated VOCs in the Southeast Asia region. There are some researchers from, I mean, local universities that involve, but I mean, personally, the Southeast Asia researchers are limited working in this field. So so what Lily noticed, it's true. I mean, we have to. I mean, of course, other fields are equally important, but Team 2 is much less explored. I mean, work on. Yeah, I feel that too. Yeah.
Yeah, I mean, we could, the SOLAS, I mean, SOLAS has been sponsoring the gas transfer symposium. Yeah, so we could, easily make the connections with the Southeast Asian community. So those group of people,
Right.
All right, is there anything else that the panel want to share with the audience, or if the audience want to share with us?
All right, I think we want to hear something from the audience too.
Yeah.
if there are.
I think two countries that not represent here as a panelist. One is Indonesia.
Yes,
the other
exactly.
one we have a researcher from Philippines. This is island nations that we thought that I tried to find researchers from Indonesia, email them, as well as from the Philippines, but I found that not so many researchers. But I'm very happy here we have Dr. Faisal and also Professor just now presented their main finding. I don't know, Dr. Faisal want to say something about this kind of research in Indonesia, because I found there are several institutes and also faculties in Indonesian universities that also focus on marine related studies. I found Dr. Faisal is here. I don't know, is it he's busy or not?
I mean, he's in the room, but probably not available at current stage. Yeah, it's a pity it's perhaps Professor Ishaq could not join us for this panel discussion, but I think this workshop is a good start. The connections are there already, so we could just exchange with each other on a regular basis. So if there is no more information that everyone would like to share with each other, so yeah. So I will pass this over to Talib to wrap up this workshop.
Okay.
Thank you.
Thank you very much, Lily.
Thank you, Lily.
Thank you very much to all the panelists. At last, I think this is not the end. I think this is the beginning for us to work together. So for this one-day workshop, I would like to thank our keynote presenter, Professor Minhan and Professor Zhiyu Liu, our invited speakers, Prof. Bala, Prof. Rahim, Prof. Ishaq, Prof. Punyasloke Baduri, and Dr. Kinyi Lee. And we also want to thank our moderator, Dr. Tachanat and Dr. Yu Jun Tam. Many thanks to all our presenters and all participants for attended this session. We also like to thank all the international committee members and local organizing committee for this workshop. Last but not least, I would like to thank SOLAS IPO, especially Dr. Lily, Dr. Chen Chengok, and Shafiq from Idea Center UKM. I think this person worked very hard to make sure this workshop is possible. We hope this is not the end, as I mentioned, but this is the beginning for us to work together on this interesting topic, with particular focus in Southeast Asia. We also hope to meet again in other SOLAS-related activities. As mentioned by Lily just now, we will have SOLAS Open Science Conference in September. And this conference, I think, for every 2 years. And also in early next year, we will have 6th Xiamen Symposium on Marine Environmental Science, XMS 6, organized by Xiamen University. So we hope that researchers from this Southeast Asia will also join these SOLAS-related activities. For that, I would like to thank all of you again. Thank you very much and have a nice day. Thank you.
Thank you, Talib. Thank you, everyone.
Yeah. Bye, everyone. Thank you very much.
Thank you. Bye-bye.
Thank you. Bye-bye.
Thank you, Prof. Talib. Thank you.
Bye.